Right this second, somewhere in the vast silence beyond Mercury's orbit, an object from another star system is racing toward our Sun at more than 200,000 kilometers per hour. A dark, tumbling shard of interstellar debris, or perhaps something more deliberate. If these mysteries have you on edge the way they have me, don't just watch, join the hunt. Hit like and subscribe so you don't miss a single revelation as this story unfolds moment by moment in real time. Tell me in the comments where you're watching, from what time it is there, and whether you believe we're hearing the whole truth about what's unfolding above our heads. And if you want to keep the signal alive, share this video on X, Facebook, Reddit, or even just with the people who still look up at night. You are the reason we can keep following the impossible, and for that, thank you. It has a name now, 3I Atlas. That's the formal catalogue number astronomers give to a discovery that defies boundaries, the third confirmed visitor ever recorded entering our solar system from the interstellar void. And in exactly 12 days, on October 29th, it will reach its moment of closest approach to the Sun, the perihelion. A passage so near that the object will graze the outermost fingers of the solar corona, skimming through a furnace of plasma millions of degrees hot. Across the world, telescopes track its faint glimmer. In Hawaii, in Chile, and the high desert of Namibia, operators whisper numbers across radio channels, coordinates, magnitudes, timestamps. Each measurement adds a brushstroke to the orbit, a line drawn across the fabric of space-time. And in a quiet office in Cambridge, Massachusetts, Professor Avi Loeb, chair of Harvard's astronomy department and founder of the Galileo Project, studies that line with something close to unease. He's seen this pattern before, not in the exact shape of an orbit, but in the tension between coincidence and intention. Because the math suggests something extraordinary. The trajectory of 3R Atlas doesn't look random. It threads through our solar system almost perfectly aligned with the ecliptic plane, the invisible disk where all major planets circle the Sun. For most comets and interstellar objects, the angle of approach is wild, chaotic. They dive in from above or below, cutting through our system like cosmic spears. But not this one. This one approaches as if it knows the lanes of traffic. For weeks, scientists have debated whether that's merely celestial luck or something altogether stranger. For Loeb, the possibility that 3 Atlas might not be a simple comet is worth considering, not because he wants it to be artificial, but because the evidence refuses to settle comfortably into the familiar categories. He remembers 2017 when another interstellar traveller, Oumuamua, blurred through our skies and vanished before telescopes could fully catch its secrets. The world debated whether it was rock ice or relic, a natural fragment or a probe from elsewhere. Now, 8 years later, another visitor comes brighter, larger, and moving on a path that promises both revelation and frustration. At observatories worldwide, the hum of tracking systems fills the night. The radio dishes at Greenbank sweep the heavens, their motors whining softly against the wind. At the Atacama Large Millimeter Array, signals ripple across an array of parabolic mirrors as the cold desert air carries the faint scent of dust and ozone. Somewhere a data engineer checks the feed from a heliospheric imager, watching static flicker across the monitor like heartbeat noise. Solar weather forecasts predict moderate flares in the coming week, bright storms that may disrupt communications, but also illuminate the Sun's edge, the place where 3I Atlas will make its slingshot dive. For astronomers, this isn't just a routine event. It's a chance to watch interstellar matter interact with our star up close, something that happens maybe once in a human lifetime. For everyone else, it's an unfolding mystery. What is this thing? A frozen mass of ancient dust ejected from a dying star system, or a hollow shell built for endurance gliding between suns as patiently as spores drift between worlds? For now, all we know is motion, relentless, silent, unstoppable. Every hour it travels another 180,000 kilometers closer, crossing the orbital paths of Earth, Venus, and Mercury. By the time you finish listening to this sentence, it will have moved thousands of kilometers deeper into the Sun's gravity well. Loeb's latest calculation reveals a subtle deceleration so faint it might be statistical noise, or it might be something else entirely. He doesn't make declarations, he asks questions, the kind that feel both thrilling and unsettling. Could the object be using the Sun's gravity to slow itself down, and if so, why? In cosmic terms, we are spectators, watching a race toward fire. But on the control room monitors, amid the quiet hum of machines, it feels like watching a door slowly close the door to direct observation, because soon the object will pass behind the Sun, hidden by its blinding glare. For several weeks, no telescope on Earth will be able to see it, The solar orbiter probes will be too far to help. A period of darkness will fall, not literal night, but an observational blackout. And when 3i Atlas emerges again, its path might not be the same. Outside, the autumn air of Earth carries no hint of the storm inside the solar furnace. Children sleep unaware that far beyond their sky, a traveller from another sun is threading a line through cosmic gravity toward ours. 12 days. That's all that separates speculation from discovery, and the scientists watching this descent know once it passes that threshold, nothing we assume about the universe will feel entirely secure again. The question that shook the observers. Every so often, astronomy encounters a question that refuses to stay polite, one that does not merely add to our knowledge but threatens to rearrange it. For Avi Loeb 3, and Atlas is that kind of question. On paper, the math should be simple. When an interstellar object enters our solar system, gravity dictates its behavior completely. The sun pulls it inward, accelerating it until the object slingshots back into the dark on a hyperbolic trajectory never to return. The curve is predictable, elegant, absolute, but the latest telemetry from 3i Atlas shows something that shouldn't be there, a subtle deviation from expectation, a slight slowing as it approaches perihelion. It's small enough that most astronomers call it noise, a flicker in the data. Loeb, however, has learned that sometimes the universe whispers its biggest surprises in the softest margins. He begins to ask a question that unsettles even his colleagues. What if this object isn't just falling toward the sun, but manoeuvring to the untrained ear that sounds like science fiction? But Loeb's reasoning is rooted in celestial mechanics itself. He invokes a principle discovered a century ago, the Oberth effect, named for Hermann Oberth, one of rocketry's founding thinkers. When a spacecraft fires its engines at the bottom of a gravity well, when it is moving at its highest velocity, each unit of propellant multiplies its effect. The deeper the dive, the stronger the slingshot. In theory, a probe diving close to the sun could perform a reverse Oberth maneuver, firing at perihelion not to gain speed, but to shed just enough of it to be caught in solar orbit. It would be like braking a roller coaster precisely at the point of maximum plunge. The sun's gravity would do the rest, transforming a fleeting visitor into a permanent resident. Loeb runs the numbers. The energies involved are enormous, yet not unimaginable. Humanity has already launched probes that exploited similar dynamics. Voyager's gravity-assist Parker solar probes' hellish sweeps past the corona, each a dance with motion and heat. If we can imagine it, could something older, more advanced have done the same long ago? To many astronomers, that's a bridge too far. The field still bears the scars of earlier embarrassments, moments when imagination sprinted ahead of evidence. But Loeb reminds them that skepticism and curiosity are not opposites. They are two sides of the same discipline. History provides its parallels. In 1910, when Halley's Comet returned after 75 years, newspapers warned that its cyanogen gases might poison Earth's atmosphere. Panic spread. Citizens sealed their windows, merchants sold anti-comet pills, and astronomers struggled to calm the public with data instead of fear. What emerged from that episode was a hard lesson. Humanity's understanding of the cosmos is often accompanied by our terror of it. Then came Oumuamua in 2017, the first confirmed interstellar object ever observed passing through our system. It tumbled irregularly, showed no visible tail, and most mysteriously accelerated slightly as it receded from the sun, as though propelled by a force no one could yet define. Solar radiation, pressure venting gas, or something else entirely. The debate raged. Loeb suggested the possibility of a thin artificial light sail, and overnight became both headline and heretic. Now, 8 years later, another anomaly has arrived. Larger, brighter, moving on an eerily aligned path, and again the data resist easy explanation. At the European Southern Observatory, teams feed new measurements into simulation clusters, watching coloured orbits spiral on screens like strands of cosmic DNA. At NASA's Jet Propulsion Laboratory, analysts debate decimal points. Could the apparent deceleration be due to observational bias, a reflection off the coma, or an unrecognised rotational torque? Every answer generates another question. Meanwhile, Loeb sketches scenarios in the margins of his notebook, a natural fragment deflecting off unseen dust clouds, a hollow object adjusting its trajectory with radiation sails, an ancient probe harvesting solar energy for braking. Each is speculative, but each is testable, and that, he argues, is the difference between fantasy and science, the willingness to measure what feels impossible. He knows how such ideas sound. He also knows that every revolution in astronomy once sounded that way. When Galileo turned his telescope skyward in 1609 and saw mountains on the moon, he upended 1,000 years of doctrine that declared celestial bodies perfect and unchanging. When Herschel discovered Uranus in 1781, the known solar system abruptly doubled in size. When Einstein's equations bent starlight around the sun in 1919, the very geometry of reality shifted beneath us. Each discovery began not with certainty but with discomfort. And so tonight, as 3i Atlas races closer to the sun, that same discomfort spreads quietly through observatories across the planet. The question has been asked, and it will not go away. If this object decelerates by design rather than accident, what kind of mind built it? And if it is natural, why does it behave so much like something that isn't? The answer could be perfectly ordinary, or it could redefine what ordinary means. For now, the only certainty is the countdown. 11 days remain. The object continues to fall, each heartbeat bringing it deeper into the furnace of our star. And somewhere between skepticism and wonder, the world holds its breath. The economy of panic. If 3i Atlas slows down, if even a whisper of evidence suggests it has stayed within the solar system, Avi Loeb warns the shock will not be confined to observatories. It will echo through boardrooms, governments, and living rooms across the planet. Because the discovery of something deliberately moving through our cosmic neighborhood would not simply rewrite textbooks. It would shake the scaffolding of everyday life, our markets, our faith in stability, our quiet assumption that humanity is the only storyteller in reach of the sun. Loeb has seen the tremors that precede such moments. He understands how quickly information becomes emotion and how emotion becomes economics. He reminds his students that data do not travel alone. They ride on headlines, on fear, on hope, and on speculation, priced into stock indexes before astronomers even finish their press releases. If 3i Atlas were to break to park itself in orbit around the sun, it would be the first time in human history that something not made by us behaved like a spacecraft within our own system. And the reaction would be immediate. Financial models would convulse. Commodities linked to satellite technology, communications, defense, and energy would surge and collapse within hours. Politicians would speak of containment and response readiness. Media networks driven by algorithmic adrenaline would flood screens with spinning 3D renderings, countdown clocks, and contradictory experts. Some would say, contact others threat. The old question, are we alone, would become a fiscal variable. Loeb doesn't predict hysteria, he predicts asymmetry. In past global scares, a minority panics while the majority freezes, unsure which experts to trust. He remembers the 1982 Jupiter effect, a sensational bestseller that claimed planetary alignment would trigger earthquakes and tidal waves. Scientists dismissed it, but fear sells faster than reassurance. For months, insurance markets in Asia quietly adjusted risk tables, and some families fled coastal cities to mountain cabins, waiting for a disaster that never came. Or the 2012 Mayan calendar panic, an artifact of misread archaeology amplified by Hollywood. As the date approached, the History Channel spoke in apocalyptic tones, talk shows joked nervously, and Google searches for end of the world peaked at 500,000 per day. On December 22nd, the sun rose anyway, but the economic footprint of that collective shiver, prepper supplies, documentaries, bunkers, was real. Multiply that by the stakes of a verified interstellar artifact. If 3i Atlas is captured by the sun remaining in a stable orbit, its permanence would demand an explanation. And in the absence of clear answers, humanity invents its own. Some would call it a divine sign. Some would see invasion. Others would see opportunity, a cosmic gold rush in data technology and patents, for decoding whatever new physics might be implied. Governments would hold emergency briefings. Defense departments would map its orbital path against satellite constellations. Astronomers would plead for calm, but public discourse would move faster than peer review. Social media would dissect each blurry image like an oracle's bone. In Loeb's private notes, there's a line that captures the unease. A discovery doesn't just reveal something about the universe, it reveals how ready we are to face it. That readiness is questionable. When Oumuamua appeared in 2017, even its faint anomalies triggered sensational headlines and conspiracy theories that still echo online. Yet no markets crashed because the object left before belief could crystallize. 3i Atlas, by contrast, offers a longer window, a deeper stage for speculation. If it lingers, the uncertainty will have time to mature into narrative, and narratives move societies. In psychological terms, the collective reaction follows a pattern known to risk theorists as availability cascades. The more vividly people imagine a scenario, the more real it feels, and the more institutions act as though it is real. A single grain of data can start an avalanche of behavior stocks, laws, sermons, hashtags, all rolling downhill faster than facts can catch up. Loeb's restraint is deliberate. He doesn't forecast apocalypse. He warns of overreaction, the human reflex to fill silence with drama. In his view, the true test is not whether the object is artificial, but whether humanity can remain scientific when confronted with the unknown. He reminds his team that in 1938, a simple radio play, War of the Worlds, convinced thousands that Martians had landed in New Jersey. Panic isn't born from evidence, it's born from imagination left unsupervised. So he waits quietly, measuring each update with disciplined calm. Around him, graduate students and data analysts talk in hushed tones about light curves and non-gravitational accelerations. Outside, news anchors are already rehearsing scripts that begin with breaking developments in space. What few notice is that the first markets to react aren't financial, they're emotional. Curiosity and fear are both currencies, and the cosmos has always been a volatile exchange. In the end, Loeb's message is simple, almost meditative. If 3Z Atlas does the impossible and stays, we will need more than telescopes. We will need maturity, the ability to greet wonder without surrendering reason. For now, the sun still burns, the object still falls, and the world still speculates. The economy of panic waits for its spark, the blind side of the sun. There is a moment in every astronomical event when vision itself fails. Not because our instruments are weak, but because the universe blinds us by design. For 3I Atlas, that moment comes on October 29th, the day of perihelion when it will slip behind the sun from Earth's perspective. In celestial geometry, this configuration is called solar conjunction. To the naked eye, the object will vanish entirely swallowed by light. For astronomers, it's a paradox bordering on cruelty. Just when the object reaches its point of greatest scientific interest, its closest dive into the sun's gravity, well, it becomes invisible. Even our most advanced optical telescopes, those that can trace faint comets beyond Neptune, are useless here. They cannot look toward the sun without being blinded by a storm of photons 10 billion times brighter than the target. Space agencies know this region as the forbidden zone. The glare saturates sensors, melts. Coronagraph filters flood CCD arrays with noise. Radio telescopes fare little better. The sun's plasma crackles across every frequency, washing over signals like surf over a footprint. For at least 3 weeks, 3 Atlas will pass through that burning silence, unseen, unmeasured, unreachable. To visualize the scale, the sun's apparent diameter from Earth is 0.5 degree, but its surrounding brightness spreads across a much wider field. For astronomers, this is a curtain of light, a perfect hiding place. If anything unusual were to occur during this period, no one on Earth would witness it directly. The scenario carries a strange poetry. For thousands of years, humanity has looked up at the sun not only as a source of life, but as a veil of mystery. Ancient civilizations believed eclipses were cosmic warnings, moments when gods demanded silence. Wars paused, kings trembled, farmers knelt. The ancient Chinese would bang drums and fire arrows into the sky to scare away the dragon they believed was devouring the sun. In Babylon, priests read the sudden darkness as an omen that could unmake empires. Today our instruments are sharper, but the feeling is the same. When the light overwhelms us, even scientists become humble witnesses to forces that will not yield to human schedules. Across observatories, preparations take on the rhythm of ritual. In Hawaii, the Pan-STARRS array calibrates for the final visible nights. In Chile's Atacama Desert, engineers review exposure sequences, knowing they have only hours before the object moves too close to the sun's glare. At the European Space Agency's control center in Darmstadt, a monitor displays a countdown 3 Atlas signal loss in 64 hours, 19 minutes, 42 seconds. Then it will be gone. Imagine the tension of that silence, a planet full of eyes suddenly blinded waiting for the heavens to reopen. It's not unlike the pause before a solar eclipse. The air grows still. Birds quiet, time seems to stretch. The light doesn't vanish at once. It drains away slowly, unnaturally, until the world feels suspended between day and night. Now scale that feeling to the size of a solar system. For decades we have built technology to see everything: infrared satellites, ultraviolet coronagraphs, solar orbiters, that brave radiation to capture images no human could survive taking. And yet here is a place our instruments cannot follow, a zone of blindness that feels as ancient as myth and as modern as encryption. During those weeks, data will stall. NASA's Solar and Heliospheric Observatory SOHO will try to glimpse the object as a faint speck in its coronagraph feeds, but even that will be uncertain. European and Chinese orbiters, Solar Orbiter, and Tianwen-1 will also lose clear line of sight. Humanity's entire astronomical network will fall silent regarding one of the most mysterious visitors it has ever recorded. To Loeb and his colleagues, the blackout is both scientific and symbolic. The moment of truth, if the object performs any maneuver, if it fragments or if it releases something smaller, will happen in that blind interval. We will have no witness, no live stream, no real-time data, only faith in our instruments waiting for them to wake up again. It is a kind of cosmic intermission, a pause that invites reflection. The last time humankind stared into such uncertainty, our ancestors looked skyward during eclipses and wondered if the sun would ever return. Now in the age of space probes and supercomputers, we find ourselves asking a similar question not about daylight, but about knowledge itself. Will what emerges from behind the sun be the same object we last saw, or will it have changed, split-slowed, or become something else entirely? In Cambridge, Loeb sums it up for his students with a quiet metaphor. Science is like standing on the shore with a flashlight. Sometimes the tide goes out and for a while the sea is dark, but the darkness is part of the rhythm. The countdown continues, the instruments prepare to blink. And for the first time since its discovery, 3i Atlas will pass out of human sight alone unwatched, carried through the furnace on the blind side of the sun. The statistical ghost. When the first orbital plots of 3i Atlas appeared on the Minor Planet Center's servers, most astronomers saw nothing more than a gracefully curved line, one of thousands sketched into the digital chart of the solar system. But Avi Loeb noticed something that made him stop. The path was too perfect. Interstellar objects are supposed to arrive from every imaginable direction, inclined, skewed, tumbling through space like darts thrown by a careless hand. They are wanderers from alien suns untethered to our plane of planets. Statistically, their inclination should scatter like stars across a globe, yet 3i Atlas slides almost exactly along the ecliptic plane, the thin invisible disk, where Earth, Mars, Jupiter and the rest of our worlds make their endless circuits around the sun. Its angle of approach barely 5 degrees off that plane. To the mind of an orbital dynamicist, that figure flashes like a siren. Imagine standing atop a skyscraper in a storm, throwing a paper airplane into the wind and watching it drift perfectly through a mail slot on a building half a city away. That is roughly the degree of precision we're talking about. For every 100 interstellar visitors entering the solar system from random directions, fewer than 2 would ever find this alignment. The universe is vast, but randomness still obeys arithmetic. Loeb's team runs a Monte Carlo simulation feeding in millions of hypothetical interstellar trajectories. The software fills screens with a storm of coloured lines, blue for ordinary angles, red for the razor-thin subset that coincide with our ecliptic. When the calculation finishes, the result is startling. The probability that such a near-perfect alignment happens by chance is less than 2%. It is quite literally a statistical ghost, an orbit that feels intentional without proving anything. To the uninitiated, the ecliptic might sound arbitrary, a geometrical accident. In truth, it's the skeletal frame of our cosmic architecture. 4.5 billion years ago, the solar system condensed from a spinning cloud of dust. The flattening of that cloud under angular momentum created this narrow disk, a galactic record groove on which the planets still play. Anything formed here travels within a few degrees of its surface. Anything arriving from elsewhere should cut across it steeply like a meteor slashing through rain. Oumuamua, the first interstellar object we ever observed, followed that logic. It dove in at a high tilt, its path indifferent to our planetary plane. The Atlas, however, behaves as if it studied the traffic lanes first and merged neatly into them. There are of course natural explanations. Gravitational focusing by Jupiter could have nudged its path, curving it toward the ecliptic. Perhaps it was deflected earlier by an encounter with another star system's debris. Space is full of invisible coin tosses. But each explanation adds layers of coincidence forces aligning across millions of kilometers to produce an outcome indistinguishable from AIM. Loeb poses it this way. If you see a bottle drifting in the ocean, you assume the waves brought it there. But if that bottle sails exactly into a harbour and drops anchor, you at least check whether someone's at the helm. Orbital mechanics itself is a patient storyteller. Objects entering the solar system at hyperbolic speeds, those unbound to the sun, follow predictable mathematics. Their velocity at infinity, their eccentricity greater than 1, all trace a simple equation of gravity and inertia. Any deviation from that script, however subtle, becomes a clue. In the data from Atlas, the Asteroid Terrestrial Impact Last Alert system, that discovered the object analysts note that its incoming velocity relative to the Sun is about 42 km per second, comfortably interstellar. But its longitude of the ascending node, the angle marking where it crosses the ecliptic, almost perfectly matches Earth's. In plain terms, it's travelling along our highway. No one can yet say why. Some scientists shrug and invoke the law of large numbers. With billions of stars and uncounted fragments drifting between them, improbable alignments must occasionally happen. Others see it differently, not as proof of design, but as a reminder that probability does not equal meaninglessness. Because history shows that every anomaly begins as an outlier. Uranus's irregular orbit led to the discovery of Neptune. Mercury's strange precession hinted at Einstein's relativity. The universe often hides revelation behind statistical oddities, still for those who work nights tracing faint dots against the background of eternity. Through Atlas feels personal, a challenge written in mathematics. In observatories from Flagstaff to La Palma, astronomers gather around monitors overlaying new points on the growing arc. Each fresh observation narrows the error bars, confirming what none of them can comfortably explain. The line stays locked within that impossibly thin corridor of the ecliptic, gliding as if on rails. It's easy to anthropomorphize such precision to imagine intent where there might be only physics. Yet even the most cautious observers admit a quiet thrill. The cosmos once again is behaving like a magician who smiles while hiding the card in plain sight. As the days tick down, to perihelion Loeb summarizes it in one phrase: "We're chasing a ghost made of statistics and it's leading us straight into the sun. The Oberth effect." To understand why October 29th matters not just to astronomers, but to the entire story of human propulsion, you must first picture the invisible landscape through which Through-Eye Atlas is falling. Space is not empty, it is shaped by gravity. Around every massive body lies a well carved into the fabric of space-time deep, where the mass is great and shallow where it is small. The sun's well is the deepest in our solar system, a bottomless radiant pit of energy that curves the paths of planets, comets, and dreams alike. Now imagine 3 Atlas as a marble rolling down the inside wall of that well. The closer it falls toward the sun, the faster it moves, gaining velocity from gravity's pull. At perihelion, it will be screaming through space at nearly 250,000 kilometers per hour, the fastest any interstellar visitor has ever been clocked near our star. Here, at the bottom of the well, physics hides one of its most elegant secrets, the Oberth effect. Named after Hermann Ober, a visionary engineer who helped define early rocketry in the 1920s, the principle is deceptively simple. If a spacecraft fires its engines while moving at high speed in a strong gravitational field, the thrust it produces is multiplied dramatically. It's not that the engine becomes more powerful, but that the kinetic energy added at the point of maximum velocity compounds like interest. A single burst near perihelion can achieve what endless burning in deep space cannot. When NASA's Voyager 2 used Jupiter's gravity to slingshot toward Neptune, it performed an Oberth maneuver of sorts, borrowing the giant planet's motion to amplify its own. The Parker Solar Probe, humanity's current record holder for speed dips repeatedly into the sun's inferno each pass, stealing a little more momentum, inching closer to a star it can never truly reach. These are dances with gravity carefully choreographed for efficiency, but 3-Eye Atlas may be performing a move no human probe has ever attempted, not a slingshot but a break. Loeb's fascination lies here. He proposes a radical possibility: what if the object intends to use the sun's gravity against itself, not to flee faster into space, but to slow down just enough to be caught? To shed velocity is to surrender freedom, to exchange the vastness of interstellar travel for a permanent orbit around our star. Why would any natural object do that? None we know of ever has, but an intelligent craft, perhaps scouting, perhaps long dormant, might. At this point, the difference between imagination and mathematics narrows to a hair's breadth. The energy required for such a deceleration is enormous, but physics doesn't forbid it. A sufficiently advanced system, say a radiation-driven sail or a fusion pulse engine, could in theory achieve the required impulse in that fiery instant when 3 Atlas dives closest to the Sun. In fact, performing it there is the smartest choice. The Oberth effect means the burn yields maximal change for minimal effort. To visualize this, imagine you're swinging on a playground swing. Push yourself at the top of the arc and you gain little. Push at the very bottom when you're moving fastest and the same force propels you much higher. That's the Oberth effect scaled up to cosmic magnitude. For Loeb, it's not a metaphor, it's an experiment the universe might be running right now. If the object does nothing, it will speed past the Sun and vanish forever, its hyperbolic trajectory flinging it back into interstellar darkness. If it performs even the slightest deceleration, an infinitesimal nudge, its orbit could shift from an escape path to a bound ellipse, transforming a brief visitor into a solar system resident. That's the fork in the road, written not in myth, but in Newtonian calculus. Around the world, supercomputers simulate possibilities. What happens if the deceleration is 0.1% or 1% or 5% of current speed? Each scenario yields a different destiny. Some results show capture in a long looping orbit that grazes the outer planets every century. Others show a chaotic trajectory that might bring it near Earth in a few decades. And then there are the rare cases, the ones the simulation teams whisper about late at night, where the object stabilizes in a near-solar orbit hidden perpetually in the glare of the Sun, a dark speck circling unseen. Human spacecraft have flirted with such elegance, but only imperfectly. The Voyagers, the Pioneers, the New Horizons probe each borrowed, gravitational boosts each hurled itself outward in triumph. But none have mastered deceleration through gravity's own energy. To slow down near a star instead of escaping it would represent an entirely new chapter of propulsion science. It would mean that somewhere, someone or something understands the Sun not as an obstacle but as a tool. And so Loeb's question isn't merely is it natural, but is it teaching us? He tells a reporter over coffee one morning, if an object from another star can use our Sun to change its course, it will be the most advanced demonstration of physics humanity has ever witnessed, performed without a single witness. It's not the fear of aliens that haunts scientists, it's the awe of witnessing an idea so profound that it reduces our ingenuity to apprenticeship. In 12 days, at the edge of that blazing gravity, 3 Atlas will reach its maximum speed and perhaps its decision. If it remains silent, nature continues her course. If it burns even briefly, history begins a new chapter. Somewhere in the black vault of space, an interstellar traveler plunges toward the heart of our solar system. The Sun awaits its light, ready to reveal or to conceal the next movement in the oldest equation of all energy, motion and intent, the window of maneuver. Suppose 3 Atlas reaches perihelion, and at that exact breath-held instant fires. Not much, not the furious blaze of a chemical rocket, just enough. Because at the bottom of the Sun's gravity, well enough is a generous word. The Oberth effect turns modest thrust into outsized consequence. A short burn at peak velocity can tip a hyperbola into an ellipse, converting a one-time flyby into a home address. Could it stay under the right conditions? Yes. Even a small delta V at perihelion could reduce the object's excess speed so that the Sun's gravity binds it. The energy cost is still immense by our standards, but the physics is friendly in that particular incandescent moment. What would produce that impulse? Here the mind inventories every known and half-known method of pushing against the void. 1. Electric propulsion ion drives. Humanity has field-tested this path. Deep Space One and Dawn used xenon ions accelerated by electric fields to generate whisper thrust for months, stacking up remarkable total velocity change. Ion engines are miserly with propellant and astonishingly precise. Their downside is power to push harder, you need more electricity. If 3i Atlas carries a high-power electric system far beyond Dawn's kilowatt-class feed, it could time a concentrated perihelion burn to great effect. A few minutes of high-power ion thrust at maximum speed accomplishes more than days of pushing in deep space. 2 solar thermal or solar electric hybrids. Near the Sun, photons and heat arrive like a tide. A craft that can drink that energy unfurling heat-resistant mirrors or plunging a working fluid through a solar furnace could convert it into thrust. Solar thermal concepts store absorbed heat and expel a superheated propellant for a brief muscular impulse exactly when the Oberth dividend is richest. Solar electric systems would instead feed huge arrays to ion thrusters, trading brute force for control. Either way, perihelion is a feast for power-hungry engines. 3. Nuclear fission microreactors. We already fly radioisotope thermoelectric generators, RTGs, that sip plutonium's warmth to make electricity for decades. But RTGs are power poor. A compact fission reactor, by contrast, could deliver sustained megawatts to electric thrusters, and do so in the darkness between stars. If the visitor houses such a heart, its perihelion burn could be crisp, measured and repeatable, more a surgeon's incision than a fireworks display. 4. Fusion or pulse concepts. Beyond our demonstrated reach lies the dream-tier compact fusion or pulsed micro-explosions channeled by magnetic fields. The appeal is obvious: enormous specific impulse and energy density. If someone older elsewhere learned to bottle a star's trick at the size of a ship, perihelion becomes a stage where the sun provides the geometry and the craft provides the will. 5. Photon pressure and sails. Icaros and Lightsail 2 proved that sunlight itself can push a craft. Close to the sun, that pressure swells. A sail can't explode into speed, but near perihelion even sailborne adjustments matter. Twist a few degrees bank into the flux, and the geometry gives back more than you paid in control effort. If 3i Atlas were a hollow shell with reflective interior geometry, it might even redirect heat and light internally to create a crude radiation-driven thrust, a star-powered whisper at the perfect time. Which of these could an interstellar object plausibly use? The honest answer is any that conserve propellant and exploit timing. The sun does the heavy lifting, the vehicle supplies finesse. From here, a cautious analysis helps separate theatre from physics. A hyperbolic passerby arrives with excess velocity, the speed it will still have far away, even after the sun has finished pulling and releasing. To be captured, the craft must cancel that excess. Spread across astronomical distances, that's a mountain. Spent at perihelion, it's a steep, walkable hill. The trade isn't magic, it's mathematics. Energy added or removed at high speed yields a larger change in orbital shape than the same energy used elsewhere. This is why the window of maneuver is so narrow, not just in space, but in time. The useful zone may last minutes. The craft must survive brutal thermal loads, hold attitude within hair-thin tolerances, and deliver its impulse on cue. Miss the window and the chance is gone for millennia. Hit it and you have turned a drive-by into a long conversation. Set that against human milestones and the picture gains texture. We learn to borrow worlds, Voyager stealing momentum from Jupiter-Saturn, Uranus-Neptune, Cassini tracing gravity's stairwell around Saturn's moons. We learn to sip fuel Dawn coaxing double-digit kilometers per second of delta V from ions no stronger than a human handshake. We learn to ride light Icaros and Lightsail angling against photon winds. We learn to kiss the Sun Parker solar probe threading ever closer ellipses through the corona's incandescent breath. But we have not yet learned to brake at a star. That last step, deceleration by design in a stellar gravity well, would be a debut performance on the grandest stage. If 3i Atlas does it, the lesson is immediate propulsion is not only a matter of engines, it's a matter of where and when you spend your courage. What about power? Even the gentlest ion burn demands electricity, and perihelion is a punishing place to run hot systems. A heat-tolerant radiator, lattice liquid metal loops, ablative baffles, all could keep a reactor or solar electric stack within survivable margins, while it squanders precious seconds for maximum effect. If the vehicle is shell-like, empty at its core, the cavity itself might be a thermal buffer and a structural trick strength at low mass, with room for sails, heat exchangers, or propellant films spread like dew across interior membranes. Engineers listening to this will feel the tug of numbers. Good. Because the ore here is not mystical, it's analytical. If the craft's excess speed is trimmed even slightly at the right instant, the sun's gravity does the rest, drawing the new ellipse like a loop of ink around a flame. The difference between escape and belonging could be a nudge small enough to hide in the glare, and if it stays, the consequences ripple outward. A captured interstellar body, natural or not, becomes a permanent lab composition, outgassing physics surface microstructures weathered by alien suns. If it's maneuverable, that permanence becomes dialogue. Planetary defense models, mission design textbooks, even energy policy would feel the aftershock. Imagine planning a probe that uses perihelion braking as casually as we now use a lunar flyby. Imagine beaming power to a sail that skims the corona, harvesting the Orberth dividend like a seasonal crop. Of course, it may do nothing. It may scorch past unchanged a textbook hyperbola, scribbled once and forgotten. That outcome is science too, a boundary drawn, a theory declined. But the possibility that it could choose differently is what holds us. Because if a traveller can turn falling into staying, if it can turn the sun into a brake instead of a whip, then it demonstrates a mastery of motion we are only beginning to sketch on blackboards. Analytical or two words that seldom fit together, and yet here they do. The analysis says it's possible. The ore says, watch anyway. Somewhere beyond the blue noon of our skies, three-eye Atlas descends toward the brightest crossroads in physics. Engines, if it has them, must be patient. Timing, if it seeks it, must be perfect. The window of manoeuvre opens once like an eyelid. What happens inside that blink could anchor a stranger to our sun, or send it away forever, a dwindling dot in the long night between stars. The night of invisibility. The countdown to October 29th does not end with fireworks or a burst of revelation. It ends with blindness. As Thrusum Atlas plunges behind the sun, Earth will lose sight of it entirely. For perhaps 3 to 4 weeks, depending on orbital geometry and solar weather, the object will vanish into radiance so overwhelming that even our best instruments, our billion-dollar eyes, will be rendered useless. This is the paradox of astronomy. The closer something draws to the light, the less we can see it. To the public, it sounds almost poetic, the object hidden by the sun. To scientists, it is torture. In Haleakala, Hawaii, the operators of the Atlas survey the very system that discovered the object, prepare for shutdown. The telescope domes glint under morning mist as engineers run final calibrations, knowing they are recording the last usable coordinates before the signal dissolves into daylight. A technician with a cup of cold coffee mutters, "We're watching it disappear." The hum of the cooling fans becomes the only sound. Half a world away in the Atacama Desert of Chile, twilight glows orange on the sand. The team at the Very Large Telescope runs their last exposure series before the sun's glare floods the cameras. They stretch across consoles, studying streaks of light that are half data, half goodbye. The air smells faintly of ozone and desert wind. Someone sets an alarm on their phone for the estimated moment of perihelion, even though they know they won't see it. In Pune, India, the UK Girawali Observatory finishes its final tracking session. Graduate students stand on the rooftop watching dawn swallow the stars one by one. One of them, barefoot, hair uncombed after an all-nighter, whispers a small prayer that it's just a comet after all. His professor beside him says nothing. He has seen decades of comets come and go, but never one from another star behaving quite like this. Soon the object will enter what astronomers call conjunction silence, a blackout zone defined by geometry and glare. The sun occupies a patch of the sky so luminous that all else within a few degrees becomes invisible. Even the mighty James Webb Space Telescope, stationed far beyond the moon, must avert its gaze. Its mirrors cannot risk the sun's unfiltered blaze. The SOHO and Stereo Solar Observatories will continue to watch the corona, but their coronagraphs are blind to objects beyond a narrow field. The instruments built to study the sun cannot see through its light. The irony is exquisite at the moment when the greatest mystery might unfold. The universe throws a curtain across the stage. The scientific world adjusts its routines. Observation schedules pause. Data pipelines empty. Across continents, chat servers and Slack channels go quiet except for short messages. Last confirmed visual 04:12 UTC. Signal faded below magnitude 22. End of track, see you on the other side. The tone is neither fear nor excitement, it's reverence, the calm that precedes both. Astronomy has always contained this rhythm of light and silence. Thousands of years ago, before telescopes, night watchers in ancient India, China and Mesopotamia performed similar vigils, tracking the movements of wandering lights across the sky, then waiting through the days when the sun hid them. They lit fires on hilltops, carved notches into stone-counted sunsets until the stars returned. Their records etched in bone clay or papyrus capture the same paradox modern astronomers now feel to understand the heavens. One must sometimes accept darkness. Loeb calls this period the night of invisibility. He uses the phrase half in jest, half in awe, because during these weeks, no one, no telescope, no satellite, no radar will truly know what Thor Atlas is doing. It will be like losing contact with a probe you never launched. Could it fragment under heat? Could it slow down? Could it release something smaller? Every possibility will unfold beyond our gaze in the bright silence on the far side of the sun. In Cambridge, Loeb sits in his office at midnight staring not at the sky but at numbers on a screen. The graphs are flat now, no new data coming in. He types a note into his digital log. From this point forward, all observation ceases. The universe will have its privacy. Outside October, rain taps softly against the window. Elsewhere, telescopes sleep under their domes, sealed against sunlight. It feels almost like an ancient ritual, billions of dollars worth of technology bowing their lenses, letting the cosmos proceed without witness. When humanity first feared eclipses, we thought the gods demanded quiet. Now we impose it ourselves because physics demands it. And so begins the longest 3 weeks in modern astronomy, a collective holding of breath while a traveller from another star passes through the unseeable. In the data centres of Europe and the Americas, servers hum idly, their algorithms looping on empty sky. Astronomers exchange dry jokes about being unemployed by sunlight. But beneath the humour lies something primal, a shared awareness that they are blind, and that blindness is both limitation and invitation. Because when the light fades again and 3 Atlas re-emerges into view, the universe will either look exactly the same or quietly forever changed. The paradox of weight. Before the blindness began, before 3 Atlas slipped behind the sun, there had been a moment that defied arithmetic. It happened on October 3rd during the Mars flyby. The object passed within 29 million kilometers of the red planet, a perfect opportunity to test one of physics' simplest expectations, that every mass, no matter how exotic, should tug on other masses according to the universal law of gravitation. But the numbers refused to play along. Every spacecraft orbiting Mars, the Mars Reconnaissance Orbiter, MAVEN or Tianwen-1, and the European Trace Gas Orbiter was watching. Their instruments are precise enough to register the gravitational tug of a passing asteroid the size of a mountain. Yet when 3 Atlas swept by, their telemetry showed nothing. No measurable wobble, no minute deflection in the Martian satellite's orbits. The data were flat. If this visitor were as massive as its brightness implied, some 30 billion tons, roughly the combined weight of 5,000 Great Pyramids of Giza, its gravitational influence should have been obvious. Mars would have quivered by millimeters, instruments would have recorded tiny oscillations, and scientists would have celebrated the clean, predictable proof of Newton's laws at interstellar scale. But there was silence. The object's apparent mass-to-light ratio simply didn't make sense. It was in Loeb's phrase, like watching a cruise ship cast no wake. To understand the puzzle, imagine standing on a dock and seeing 2 ships on the horizon, one gleaming and vast, the other small and dull. You'd assume the larger vessel displaces more water, makes the bigger wave. But in this case, the bright grand object left none at all, while the faint ones around it did. For scientists, that contradiction between how much light it reflects and how much gravity it exerts is an open wound. This is not the first time celestial objects have tricked us with weight. When Edmund Halley's comet returned in 1910, astronomers calculated its density based on brightness and orbital behaviour. The result was so low that some joked it must be more empty than fog. Decades later, we confirmed that comets are not solid mountains but fragile porous assemblies of ice and dust, dirty snowballs evaporating as they approach the sun. Yet even Halley's ethereal body exerted predictable gravitational influence. It pulled at other objects exactly as its meagre mass required. The refrain iron Atlas, by contrast, seems to weigh less than nothing it shines like. Its albedo, the measure of how much sunlight it reflects, suggests a surface rich in dust and ice, perhaps metallic in places. From this, astronomers estimate a size between 5 and 46 kilometers wide. That's enormous, but the gravitational signature suggests a density closer to aerogel than rock, lighter even than foam. Something doesn't add up. One hypothesis is that it's composed of extremely porous material, perhaps ice mixed with vacuum cavities, like cosmic pumice. Another proposes that the brightness is deceptive. Maybe we're seeing jets of gas or reflective dust, making the object appear larger and denser than it is. But the simplest interpretation, when all ordinary options fail, is the one that makes scientists uneasy. There's far less inside it than there appears to be. This is what Loeb calls the paradox of weight. An object that shines like a mountain but weighs like a feather. To visualize this, he offers his students an image. Imagine lifting a golden balloon. It glitters as if it were solid metal, but when you hold it, it drifts upward instead. If nature has truly crafted something this hollow, it's unlike any comet ever catalogued. But nature has surprised us before. In 1994, the world watched the fragments of Comet Shoemaker-Levy 9 slam into Jupiter, 21 separate pieces torn apart by tidal stress weeks earlier. Before the impacts, astronomers realized the comet had split far too easily. Its internal cohesion was weaker than chalk. Jupiter's immense gravity had simply stretched and shattered it. That event revealed that many comets are loose aggregates held together by frost and faith not solid boulders. When pressure mounts, they crumble like old snow, yet even Shoemaker Levy 9's ruins obeyed gravity to the last decimal place. They fell, they burned, they left scars on Jupiter's clouds. They were fragile but not impossible. This such atlas goes further, it seems to deny mass itself. When Loeb first saw the readings from Mars orbiters, he ran the math 3 times. Each recalculation produced the same result, negligible gravitational influence, despite immense apparent size. A colleague joked, "Maybe it's made of styrofoam." Loeb didn't laugh. "If it is," he said, "then the universe has better engineers than we do." The term hollow still sounds heretical, but the physics points toward missing matter, an interior void vast enough to reconcile brightness with invisibility to gravity. If that's true, then the surface we see is only a shell, a skin of material wrapped around empty space. Such an object could not have formed in the chaotic birth of a star system. There's no natural process we know that hollows a comet from within without shattering it. Unless, of course, it was built that way. And so the Mars flyby meant to yield reassuring data became the moment the mystery deepened. Instead of confirming that this visitor was a solid relic of another sun, it suggested that it might be something else. A structure disguised as a rock moving as lightly as light itself. In labs and lecture halls, scientists continue to reanalyze the telemetry hunting for overlooked forces outgassing magnetic fields, radiation pressure. But the models remain stubborn. No tweak restores gravity's missing footprint. The paradox remains suspended in the data like a mirage, a bright thing that weighs almost nothing, a heavy-looking ghost that leaves no trace, a traveler that bends light but not planets. Whatever 3i Atlas is, it moves through our solar system like a secret, pretending to be ordinary, shining brilliantly yet leaving the cosmos untouched. The hollow impossibility. When the last fragments of data from the Mars flyby were compiled, Avi Loeb faced a riddle no equation could domesticate. The object was bright enough to suggest substance, but its gravitational influence was so faint that it might as well have been a reflection, not a thing. There was one way to reconcile those extremes: take away the inside. The logic was brutal in its simplicity. If 3i Atlas were truly solid, its brightness, volume and rotation should interlock through familiar physics. A dense body spins within a narrow range, its mass stabilizing it like a gyroscope. But the visitor's measured rotation rate was too slow for any object of that apparent size and density. It turned lazily, completing a full spin in far more hours than its mass could permit without tearing apart. Inertia and cohesion refused to match. Loeb ran the parameters through dynamic stability models, adjusting for reflectivity, surface roughness and possible jets of gas. The numbers held firm. Only by removing most of the interior mass could the equations balance. The math whispered a phrase that still feels heretical: it is hollow. To most astronomers, hollow sounds like pseudoscience, a word reserved for myths about hidden moons and glass planets. But Loeb's usage is literal and precise: an internal cavity large enough that the remaining shell supplies the observed rotation and luminosity without corresponding gravity. If that is true, then we are witnessing a category of object never confirmed before, something neither asteroid nor comet but structure. The comparison comes naturally. Human engineering has dreamed of such forms for a century. In 1929, J.D. Bernal imagined spherical space habitats, Bernal spheres rotating to simulate gravity housing entire civilizations. Decades later, physicist Freeman Dyson proposed vast energy-collecting megastructures encircling stars, Dyson spheres, and Dyson swarms, machines of light, built to harness the full output of a sun. Science fiction adopted these ideas eagerly. Physics never forbade them, only economics did. Now in Loeb's calculations, nature or something that uses nature seems to have drawn a faint blueprint of those human dreams, a shell large enough to sail between stars. Consider what hollow really means in this context. The density derived from 3i Atlas's orbit and brightness hovers near 0.001 GBZ SEM3 lighter than the foam in a cappuccino lighter, even than the aerogels that insulate spacecraft. A natural comet might reach a tenth of that density at best before crumbling. Any lower, and sunlight pressure should blow fragments away like dust. Yet the visitor holds together, stable, coherent, indifferent to the sun's fury. To achieve that, it must distribute stress flawlessly across its surface like an eggshell scaled to kilometers. In mechanical engineering, that geometry thin, strong, curved is efficient because it transfers load across tension rather than compression. If the object's skin were carbon-rich metallic or reinforced by complex lattice structures, its resilience could be extraordinary. And that's the unnerving part the design works. Picture it in slow motion, a dark ellipsoid perhaps 5 kilometers across, tumbling silently through solar light, its outer layer glinting in a rhythm that hints at panels or facets. Spectrographs show mixed signatures. Dust ice maybe trace metals but nothing definitive, yet the balance of its motion tells a deeper story than chemistry can. The hollowness explains everything that solidity cannot: the paradoxically low mass, the slow rotation, the gravitational invisibility, the uncanny orbital stability. Each anomaly aligns once you imagine absence where mass should be. Of course, absence alone doesn't prove artifice. Cosmic processes carve cavities, some comets are honeycombed by sublimation. Asteroids can become rubble piles with central voids. But no known mechanism produces an evenly distributed kilometer-wide hollow without structural collapse. Nature makes fragments, not architecture. Loeb knows this, and yet he treads carefully. His papers phrase it in the language of restraint, a non-uniform internal density model with significant central void. But privately, the thought persists. What if we are glimpsing engineering by erosion or by intent? A craft built to look accidental, its shell masquerading as debris. In seminars, skeptics remind him that extraordinary claims demand extraordinary evidence. He nods, unoffended. Yes, he says, and extraordinary data demand imagination equal to their scale. He isn't declaring alien design. He's expanding the hypothesis space the same intellectual courage that once allowed humanity to accept that the Earth moves, that light bends, that the atom is empty space with pattern. Because at every scale, reality has turned out to be hollower than intuition. Atoms themselves are almost nothing, 99.99% vacuum surrounded by probability. Galaxies too are mostly void stitched together by the thin web of dark matter. Why should an artifact or a natural relic from another system not echo that cosmic pattern? Emptiness holding form. Loeb sketches a note in his journal. Perhaps hollowness is efficiency. Matter where it's needed, nothing where it isn't. That line will later circulate online misquoted as metaphor. But for him it's literal, a design principle written in starlight. If 3i Atlas is indeed a shell, its interior could once have held anything gas equipment microprobes, even emptiness itself as an insulator for travel through radiation. The possibilities outnumber our languages for wonder, and so the hollow impossibility becomes both puzzle and mirror. Whether sculpted by cosmic chance or constructed by intent, it forces us to rethink solidity as virtue. Perhaps endurance lies not in being heavy, but in being light enough to survive the fires between suns, as the object vanishes behind the sun that thought lingers on every control room screen. A hollow thing, stable in a storm of gravity, an emptiness that holds its shape. The universe once again teaches by paradox. The two impossible options. By mid-October, as 3 Atlas slipped into the blinding arc of the sun, Loeb's team found themselves cornered between two explanations, and both seemed impossible. Option 1. 3 Atlas is a natural object made of ultra-low density material lighter than any cosmic substance ever recorded. Option 2, it's artificial, a structure built to appear natural, hollow by design. Between those two walls, science is forced to stand uncomfortably still. The first option, though, less dramatic, is no less revolutionary. If 3i Atlas is natural, then it's composed of something never seen before, a solid that is almost not solid matter, so porous it's practically nothing. Imagine a snowflake scaled to the size of a mountain, each crystal separated by voids large enough for light itself to slip through unhindered. Comets we know are fragile, yes, but not that fragile. Even the fluffiest dust aggregate, even the weakest rubble pile would struggle to hold together under the sun's heat, under rotational stress, under the gravitational tides of Mars. The laws of material strength whisper such an object should have disintegrated long ago. Yet 3 Atlas persists, turning slowly, calmly, as if immune to disintegration. That's why many call this first theory the fairy snow hypothesis, beautiful, improbable, and unsatisfying. The second option is the one that draws headlines and sleepless nights that the visitor is engineered. A hollow shell, a probe, perhaps a relic drifting on autopilot through interstellar space. But to label it artificial is to invite every ghost of pseudoscience ever exiled from serious inquiry. Loeb knows this. He also knows that if he doesn't at least consider the possibility science betrays its own curiosity. Between these two options, natural absurdity and technological miracle, there is a narrow corridor called humility. It's the place where every scientific revolution begins. History is full of data once dismissed as errors because they didn't fit the story of their time. In 1900, when physicists measured radiation emitted by hot objects, the numbers made no sense. Max Planck patched the math with a desperate constant of fudge factor that became the birth of quantum theory. When astronomers in the 1930s charted galaxies, their motions defied Newtonian gravity. Fritz Zwicky called the missing mass Dunkel Materie dark matter. Colleagues laughed. Now the entire structure of the cosmos depends on it. When Jocelyn Bell Burnell in 1967 saw precise pulses from deep space, she wondered if it was a hoax, even labelling her notes LGM-1 Little Green Men. It wasn't aliens. It was the first pulsar the lighthouse of a collapsed star. Each anomaly began as an embarrassment and became a revelation. Science grows not by rejecting the impossible, but by redefining what possible means. Loeb often quotes a line from the philosopher Karl Popper: "Science must begin with myths, and with the criticism of myths." To him, myth isn't falsehood, it's the horizon of imagination that guides inquiry. Without daring hypotheses, even outlandish ones, data remains inert. So he proceeds like a tightrope walker over the abyss. On one side lies the comfort of conventional explanations stretched beyond credibility. On the other, the vertigo of contemplating intent in an object that should have none. Could 3 Atlas be a conglomerate of exotic ices, hydrogen, nitrogen, or carbon monoxide sublimating invisibly to produce strange optical signatures? Perhaps, but hydrogen ice would evaporate long before reaching Mars's orbit. Nitrogen would too. Could it be an artificial shell designed to endure eons, built by a civilization long vanished? Possibly, but then why now, why here, and why in silence? Each line of reasoning collapses under its own weight, leaving a void in the middle, where evidence and imagination stare at each other unblinking. At the Harvard-Smithsonian Center for Astrophysics, the debates are almost philosophical. One researcher argues that calling it engineered insults the rigor of astrophysics. Another replies that refusing to test that hypothesis insults the rigor of truth itself. It's not belief they're after, its completeness. The discomfort runs deep because the cosmos has always been our mirror. To find design out there even without a designer in sight is to confront our own reflection. When Loeb presents his findings at a quiet symposium in early October, he ends with a slide showing 2 simple bullet points. Density inconsistency requires material science beyond current models. Structural stability implies internal reinforcement or engineered symmetry. He doesn't say alien, he says anomalous. And then he adds almost softly, if nature made this, we must learn her method. If someone else made this, we must learn their intent. That single line captures the essence of the scientific dilemma: curiosity without surrender. Outside the lecture hall, the autumn evening smells of rain and cold coffee. Young astronomers discuss the paradox in clusters, half whispering, half laughing, as though the universe might overhear. One of them muses, "We keep building bigger telescopes to see further, but maybe what we really need is bigger humility. It is not yet clear which option, impossibly light or impossibly deliberate, will survive the scrutiny of time." But in these weeks of blindness, while 3i Atlas hides behind the sun, the question itself becomes the experiment. How does science behave when faced with data that feels like fiction? The answer, as always, is slowly through patience, skepticism, and wonder. Because in the history of discovery, every impossible thing we now accept once looked exactly like this: the shell and the signature. By the time the observatories went dark, Loeb's working model had acquired a new name among his graduate students: the shell hypothesis. They said it half jokingly, half in awe, as if describing something that shouldn't exist yet somehow does. In its simplest form, the math behind it is elegant. If an object's moment of inertia, its resistance to rotational change, exceeds what its mass should allow, one can either add hidden weight or subtract the core. Subtracting the core fits the data best. The object spins too slowly for a solid body. Its rotation should have sped up or fractured under solar torques. Instead, it turns as though the mass has been redistributed to the edges, like a figure skater extending her arms to slow her spin. Every equation points toward the same geometry mass concentrated at the rim emptiness inside. So Loeb begins treating 3I Atlas not as a comet but as a shell under stress, a mechanical structure that must obey both celestial mechanics and materials science. He calls in colleagues from fields rarely connected to astrophysics, a mechanical engineer specializing in thin-film composites, a materials physicist studying carbon nanolattices, a structural acoustician who models how vibration travels through hollow domes. Together, they translate the orbit into engineering language. If the object's surface is roughly 10 kilometers across and only a few hundred meters thick, the differential heating near perihelion should have torn it apart. At its predicted temperatures approaching 1000 ORX, ordinary carbon ice or silicate dust would sublimate instantly. Yet if the shell were made of graphitic carbon silicon carbide, or even a metal ceramic alloy, it could survive briefly, especially if its spin distributed thermal load evenly across its skin. One of the engineers compares it to a tennis ball in a furnace surviving not by strength alone, but by rapid motion that prevents any one point from absorbing too much heat. The acoustician adds an unexpected insight in a hollow sphere vibrations resonate differently than in a solid one. When a micrometeorite strikes, the impact should send flexural waves ringing through the shell, changing its reflected light in measurable flickers. So the team examines the light curve anomalies, those subtle rhythmic pulses in brightness recorded before conjunction. They discover a repeating pattern, faint but real, consistent with oscillations traveling through a thin surface rather than a dense core. It is in a sense the object's acoustic signature, a kind of interstellar hum, written in photons instead of sound. If confirmed, that signature would become the first indirect measurement of an engineered resonance in a cosmic object. And yet the explanation need not be technological. The same pattern could arise from thermal cracking or layered ice. Nature too hums when heated. Still, the cross-disciplinary conversation grows electric. Material scientists run finite element stress simulations feeding estimated density rotation and solar flux into their models. The visualizations bloom across monitors, colourful stress maps wrapping around a spinning ellipsoid. Most iterations end catastrophically. The shell crumples or shears within minutes of perihelion. But a few parameter sets, those using ultra-low density carbon silicate foam, survive. The margins are razor thin, but they exist. One researcher leans back from the screen. "It's possible," she says softly but barely. Loeb smiles. Barely possible is where discovery lives. The analysis spills beyond astrophysics into architecture and philosophy. Architects know that emptiness is structure, that a dome's strength comes from geometry, not material. Sound engineers know that hollow instruments amplify, not weaken. Physicists know that atoms themselves are mostly void. Across these disciplines, the same pattern emerges: strength, through distribution, endurance, through lightness. The parallels grow irresistible. If one were to design a vessel for interstellar travel, something to survive dust, impacts, radiation and time, it might look exactly like this. A hardened shell, rotationally stabilized, perhaps once filled with payload or gas, now silent and empty. Even as a natural phenomenon, it would still rewrite what we know about cohesion at cosmic scales. At night, Loeb sketches the geometry on his whiteboard: concentric shells, tension lines, stress vectors. Then he writes a single phrase beneath them, a hollow thing that holds. He tells his students that in a way the universe itself is a shell, stars scattered thinly across an expanding void, galaxies clinging to the edges of invisible filaments, light echoing through emptiness. 3I Atlas, whatever it is, might simply mirror that cosmic architecture, a microcosm of how space builds endurance out of nothingness. And if there's meaning in that symmetry, if an object built by unknown hands or sculpted by chance embodies the same logic as galaxies and atoms, then its discovery is less an anomaly than a revelation that emptiness is not failure but design. For now, all they can do is wait for it to emerge from behind the sun to see if that fragile shell still holds. Until then, the models spin quietly on their servers, humming with equations that straddle two worlds: the world of machines and the world of stars. The dandelion analogy. When the data first suggested hollowness, most astronomers stopped there, content to label 3I Atlas a fragile comet, an overinflated relic, or a fluke of reflection. But Avi Loeb kept asking the question that made others uncomfortable: if it's hollow, what was the space inside for? That is when he proposed the analogy that would ignite both wonder and controversy: the dandelion. In one of his papers and later in a public lecture, Loeb framed the idea not as belief, but as a thought experiment, a bridge between biology and astrophysics. When a dandelion releases its seeds, he said it doesn't send one heavy kernel into the wind. It sends hundreds of light hollow spheres, each one capable of founding a new garden far away. Evolution discovered a law of redundancy. Why would technology not do the same? The metaphor struck a nerve. Imagine he suggested that an advanced civilization long vanished or still awake somewhere in the dark sought to explore the galaxy without risking crewed ships or decades-long communications. They would not send battleships or arcs. They would send seeds, small autonomous probes capable of self-repair and replication, light enough to drift on radiation pressure, resilient enough to cross interstellar gulfs. 3 Atlas. In this view would be the parent dandelion, a mothership whose hollow core once carried hundreds or thousands of these seeds. Its purpose to approach a star, use the gravitational well to decelerate the Oberth break, and then release its children into stable orbits, scattering them like spores into fertile ground. Loeb's metaphor resonated beyond science. Journalists, poets, even artists seized it, turning his quiet speculation into mythic imagery. In some retellings, the sun became a field of light in 3i Atlas, the dandelion drifting toward it ready to sow the solar system with the pollen of curiosity. But for Loeb, the point was not poetry, it was testability. If the object truly deploys smaller fragments at perihelion, those fragments would diverge from its main path with distinct purposeful vectors, unlike random debris from a cometary breakup. They might exhibit acceleration or maneuvering inconsistent with passive drift. Astronomers could watch for that signature once the object re-emerges from behind the sun, the pattern of intention hidden in motion. Still, the metaphor had power, precisely because it connected with something older than science, the instinctive logic of replication and survival. Every culture on Earth carries stories of travelers sending forth offspring into the unknown. Polynesian navigators launching canoes toward unseen islands, trusting stars and currents. Nomadic tribes scattering herds and settlements across steppes. Migratory birds crossing hemispheres guided by a geometry written in their bones. Even myths echo the same principle, gods breathing life into dust seeds cast into chaos to birth order. The dandelion isn't just a plant, it's an archetype fragility multiplied until it becomes strength. Loeb's analogy fits neatly into this universal narrative. Where biology uses genes, technology might use data. Where a flower rides the wind, a probe might ride starlight. Where evolution disperses life across continents, intelligence might disperse curiosity across stars. To explain the physics, Loeb invoked the concept of light sails, thin membranes capable of harnessing photon pressure. A seed probe of mere grams could in theory accelerate to a fraction of light speed under a steady push of starlight, then decelerate near another star using magnetic fields or radiation drag. The idea is not science fiction. Human researchers are already testing it through the Breakthrough Starshot initiative, which Loeb himself helped advise. It's not impossible, just ambitious. An ambition, he notes, is a natural law as old as biology. Skeptics countered that such seeds would be long dead, their technology eroded by millennia of radiation and dust. But Loeb reminded them spores remain viable after centuries. Tardigrades, the microscopic bears of moss, survive vacuum and radiation. Even DNA frozen in permafrost outlasts civilizations. Why should intelligence not learn similar tricks? The media predictably seized the drama, calling 3 Atlas the cosmic flower, the pollinator from the stars. But beneath the metaphor lies a profound scientific symmetry. In the same way a dandelion invests energy once to release countless children, a civilization could invest once in a fleet of microprobes that explore forever, drifting, multiplying, carried by the winds of light. And what if that civilization no longer exists? Then 3i Atlas is not an ambassador, but an orphaned ecosystem, a machine continuing its program long after its creators turned to dust. Its seeds, if they ever dispersed, might still roam unnoticed among asteroids or within planetary atmospheres collecting data, sleeping, waiting. Loeb never calls this belief. He calls it discipline of imagination. Biology and astronomy are not separate stories, he tells his students. Both are survival strategies in an indifferent universe, and so the metaphor holds simultaneously scientific and spiritual, a flower of light, drifting between suns, teaching us that replication is not vanity, it's continuity. The image lingers because it feels right in a way equations seldom do. Whether 3i Atlas is an engineered parent, a natural hollow comet, or something in between, its existence echoes the same truth that every culture has whispered since the first seeds took to the wind. That survival is not conquest. It is dispersion, the test of perihelion. Science, unlike faith, survives only by being testable, and for Avi Loeb, the beauty of the dandelion analogy lies precisely there. It's not a myth to be believed. It's a hypothesis that could in principle be proven wrong. That proof or disproof hinges on a single event perihelion, the instant when 3i Atlas dives behind the sun and skims the bottom of its gravitational well. If the hollow-shell model is correct, and if the dandelion seed hypothesis carries even a grain of truth, then perihelion is not just a pass-by. It's a moment of possible deployment, the window during which the object might release smaller companions into new orbits. And unlike theology, such an act would leave fingerprints. If the object is merely a natural comet under stress, its breakup will be chaotic, a random cloud of fragments peeling away in all directions, each following momentum, and sunlight pressure scattering like ash in a gust. The resulting debris will spread along its orbital path predictable and passive. But if 3i Atlas is a delivery system, its offspring will not behave like ash, they'll behave like pilots. Their trajectories would diverge deliberately, multiple small bodies accelerating or turning in distinct purposeful vectors. Pattern recognition would tell the story. Chaos is isotropic directionless. Choreography has rhythm. The entire astronomy community knows this is the test that matters most. At Harvard, Loeb and his collaborators coordinate with the Galileo Project's Sky Monitoring Array, designed to detect unidentified aerial phenomena in Earth's atmosphere. Though originally focused closer to home, its network of wide-field telescopes, radar systems, and infrared sensors could detect any unusual motion in space, especially if new objects appear in synchronous timing with 3i Atlas's emergence from behind the Sun. Meanwhile, the European Space Agency has programmed its solar orbiter instruments to capture coronagraph frames at slightly extended radii, pushing the sensors to their design limits in hope of glimpsing something unexpected near perihelion's edge. The NASA Stereo probes drifting on either side of the Sun will monitor for faint glints of moving light, sub-pixel shifts that algorithms can enhance. Across the planet, computers hum quietly, primed for the smallest anomaly. In Hawaii, Chile, India, Arizona, and Namibia, ground-based observatories run predictive scripts to reacquire the object once it re-emerges from the solar glare. They'll look not for one point of light, but for many. In theory, each observatory's field of view overlaps with others, creating a planetary sensor web. When an unexpected dot appears in one image, cross-checks will confirm whether it's an artifact, a satellite reflection, or a genuine new body. Within hours, data pipelines will converge, each fragment's position triangulated against the expected ephemeris of 3i Atlas. If multiple fragments appear, the pattern will reveal intent or accident. Natural breakup means random spacing along the orbital path like crumbs on a curve. Artificial deployment would form geometric distributions, perhaps radial symmetry, perhaps paired trajectories too clean to be coincidental. Even amateurs will join the hunt. With modern photometric software and internet collaboration, thousands of small telescopes worldwide can track faint magnitude changes. Each observer, though, working alone contributes a pixel to the global mosaic of detection. And then there's the infrared clue. If the object or anything released from it carries power, systems waste heat will betray them. The Neowise infrared telescope is scheduled to resume scans near early November. Its detectors can sense temperature differentials so minute they could expose a spacecraft engine firing halfway across the solar system. For Loeb, this convergence of data sources is exhilarating. The cosmos has set up a laboratory without walls, a natural experiment unfolding across interplanetary space. The instruments are ready. All that remains is the event. He describes it to his team like this: "We're waiting for the orchestra to play. If it's a comet, we'll hear static. If it's something else, there will be melody." The comparison isn't poetic exaggeration, it's a literal approach to data analysis. Machine learning algorithms trained on chaotic fragmentation patterns can distinguish randomness from rhythm. A simple comet's debris field looks statistically Gaussian noise without motif. A deliberate release would leave correlation peaks, repeated separations, equal angular spacing synchronized accelerations, in other words, composition. To human eyes, it might appear as a faint choreography across the heavens, one point of light becoming 2, then 5, then 20, each moving with faint deliberation against the solar halo. Instruments would record minute differences in velocity enough to hint at control. Even without visible propulsion, coordinated drift would be unmistakable, and that's why Loeb insists the hypothesis is scientifically fair. It's falsifiable. If no fragments appear, if the visitor passes the sun intact or breaks apart naturally, then the dandelion theory collapses under its own elegance. The beauty of science, he reminds journalists, is that even failure is illumination. But if the pattern emerges, if geometry triumphs over chance, then the world will need a new vocabulary for what has just been seen. For now, the stage is set, the sun's blinding light, the instruments in waiting, the silence before data. A global audience of astronomers, engineers and dreamers counts the days until the object re-emerges. In Cambridge, Loeb writes a single line at the bottom of his latest draft, perihelion is the test. The universe has offered the experiment, all we must do is watch faithfully. And so the test of perihelion becomes something larger than astronomy, it becomes a meditation on human patience. Because whether the sky reveals fragments or none at all, the act of looking, of expecting evidence rather than story, is the only way science honours mystery without worshipping it. The before and after experiment. Long before Three-Eye Atlas vanished into the sun's glare, astronomers built what they called the baseline, a portrait of everything they could possibly know about the visitor before it disappeared. It was in effect the universe's version of a control group, the before half of an experiment whose after was still unwritten. Every photon mattered. In observatories across 5 continents, teams collected photometric data, minute measurements of how the object's brightness fluctuated over time. Each flicker, each fractional drop in magnitude told a story about rotation, reflectivity and surface texture. A steady brightness would mean a smooth, uniform body. A repeating pulse pattern would betray a rotating, uneven one. Sudden dips could indicate jets of gas or temporary shadowing by fragments. By mid-October, astronomers had compiled over 6 million individual light curve samples, a shimmering heartbeat of numbers that mapped how sunlight danced off the surface of a wanderer from another star. The process was brutally meticulous. Every observation was corrected for atmospheric distortion, instrument noise, and the sun's changing angle. The data were then normalized across telescopes. A measurement taken in Hawaii at dawn had to match one in Chile at dusk, within thousandths of a magnitude. This global effort turned the planet itself into one vast interferometer, a single eye made of many lenses. Loeb compared it to medical imaging. Before surgery, he said, you scan every tissue. The cosmos gives us only one chance to take the MRI of this patient before it goes under anesthesia. That anesthesia would be the sun's glare. The goal was simple but profound, to know with absolute precision how the object behaved before it entered invisibility, so that when it emerged again, any difference, any twitch of brightness, new motion, or spectral fingerprint could be measured against a perfect record. In scientific terms, the baseline became the null hypothesis that nothing will change. Everything else, fragmentation, deceleration, the appearance of smaller companions, would register as deviation. It was the kind of experiment that no human designed, but all of humanity could participate in. While news outlets spun speculative headlines, the observatories grew silent, almost reverent. Night after night, they gathered photons from an object so faint it lived at the edge of detectability. At times, the data was just noise, static on a cosmic radio, but even static has structure when enough people listen. At the European Southern Observatory, a young data analyst stared at the light curve forming on her screen, a rhythmic pulse, smooth, consistent, hypnotic. It's like it's breathing, she whispered. The senior scientist beside her smiled. Good. That means it's alive, at least until the sun takes it. They laughed quietly, knowing how easily science anthropomorphizes the unknown. In Arizona, the Catalina Sky Survey's automated telescopes recorded exposures every 45 seconds, producing terabytes of faint smudges that would later be cross-correlated with radar data and orbital simulations. In Japan, the Subaru telescope's adaptive optics tried to resolve surface features pushing the limits of optical physics. Each observatory contributed a different wavelength, a different sensitivity, infrared for heat, visible for brightness, ultraviolet for dust composition. When combined, the datasets formed something extraordinary, a multispectral fingerprint of Three-Eye Atlas before its disappearance. Astronomers call this fingerprint the Phase 0 dataset. It's the cosmic equivalent of photographing a crime scene before any evidence can be disturbed. Once the object rounds the Sun, any new trace, an extra spot of light, an altered spin period, a dust tail where none existed, will stand out in stark relief. By subtraction, intention could be inferred. The concept isn't new. It's how planetary scientists detect change on Mars, or how exoplanet hunters identify new worlds. But never before has humanity performed such a global calibration for something so mysterious and fleeting. In Cambridge, Loeb described it during a live stream with quiet pride. "We're running a controlled experiment with the universe. We have the before, nature will supply the after, and we won't get another chance." He compared the operation to the Michelson-Morley experiment of 1887, which disproved the existence of the luminiferous ether. That too was an experiment whose power lay in precision, showing not what existed but what didn't. The baseline thus becomes a philosophical anchor. If nothing changes, it confirms that the anomaly was illusion, a cosmic coincidence resolved by better data. If something changes, it reopens the question of agency. Every graduate student working on the project knows this duality. They call it the coin of reality. Heads were wrong, tails were transformed. Either way, knowledge wins, and there's something poetic about the timing. The same sun that blinds us will also erase and rewrite the visitor's signature. When 3 Atlas emerges again, it will carry the traces of whatever happened in that hidden theatre of plasma heat light silence or revelation. In the language of science, this waiting period is merely data gap dt, the time between 2 observations. But to those watching, it feels like the pause between inhale and exhale, the moment before a heartbeat resumes on the monitor. The cosmos for once has given us a clean experiment, before and soon after. The breakup or birth. In the long blinding silence of solar conjunction telescopes around the world slept under their domes, data streams flatlining into stillness. And then one morning in early November, the sun moved just far enough on the ecliptic for the first instruments to open their eyes again. When the feeds came back online, the sky looked the same until it didn't. At first, the images were barely more than static, a field of stars, dust, noise. But buried in the data from the stereo spacecraft analysts noticed a faint smear trailing the re-emerging 3I Atlas, a delicate plume that seemed to fan outward like a comet's tail, except the pattern wasn't random. It was segmented. 3 bright knots of light evenly spaced drifting just behind the primary object. The first reaction was denial. Cosmic rays, digital noise, instrument error. There were 100 reasons not to believe. But as more observatories regained vision, the solar orbiter, then ground-based telescopes in Chile and Namibia, the pattern persisted. 3I Atlas was no longer alone. The question wasn't what they were seeing, but why. If it was a natural fragmentation, it would follow the same chaotic choreography comets have performed since the dawn of the solar system. We know this dance well. Pressure builds as sunlight heats volatile ices beneath the surface. Internal gas pockets rupture, the nucleus fractures, and pieces drift apart in a spray of dust and frozen vapor. Their motion is random, dictated by chance. Some shards accelerate ahead, others lag behind, some vanish entirely. The resulting formation looks like a broken necklace, uneven and unrepeatable. But this was different. The 3 points moved with uncanny symmetry. Instead of scattering, they maintained their spacing like satellites holding formation. The intervals between them stayed constant across hours of observation, and their relative brightness fluctuated in rhythm as though spinning in phase with the parent body. To the naked eye, it could have been coincidence. To the mathematician, it was pattern. Loeb's team overlaid the new data on the Phase 0 baseline from before the blackout. The difference was breathtaking. Where there had been one steady pulse of brightness, now there were 4 each echoing the other like voices in a choir. Either the object fragmented too perfectly, one researcher whispered, or it just gave birth. No one dared to say the word deployment. For days, the world's observatories focused on that quadrant of sky racing to collect every photon before the object faded into distance again. Light curve analyses came back from Hawaii spectral models, from Chile radio readings from Australia. Each seemed to hint at the same impossible narrative. The fragments were not just drifting, they were adjusting. Tiny, consistent deviations in velocity on the order of centimeters per second appeared in the telemetry, suggesting microthrust or directed momentum. There are natural mechanisms that mimic control. Outgassing jets from uneven ice pockets can push fragments like miniature thrusters. Dust reflections can fake acceleration. Radiation pressure can sculpt coincidences into order. Yet each alternative demanded its own chain of unlikely coincidences, so many that the simpler explanation for once began to sound like intent. It was the paradox all over again. Either physics was behaving in a way never before seen, or someone or something was using physics precisely as it was designed to be used. From a technical standpoint, the imagery was mesmerizing. High-contrast processing revealed faint filaments, connecting the fragments, possibly dust trails, possibly ejecta, but their alignment looked almost architectural, forming an arc of equidistant points that curved gently away from the sun. In the simulation labs, engineers modeled what it would take to reproduce such a pattern intentionally. A hollow mothership releasing 3 smaller modules at perihelion, each coasting outward on its own vector, would fit the data perfectly. The timing energy and geometry all lined up with Loeb's dandelion hypothesis. The news leaked before peer review. Within hours, headlines around the world screamed, "Did the sun's visitor reproduce Loeb? Avoided the spotlight, preferring numbers to narrative." In his office, he and his students plotted trajectories in quiet awe. If the pattern held, it could only have been orchestrated within seconds of perihelion, the precise moment Earth was blind. The sun itself had hidden the act. Emotionally, it was almost unbearable to contemplate. Astronomers are trained to remain detached, but when nature or technology behaves with apparent grace, the human heart refuses to stay still. Watching those synchronized points of light glide through the dark was like seeing handwriting appear on glass, too deliberate to be coincidence, too unreachable to confirm. Every new image fed both belief and doubt. Some frames showed the fragments dispersing slightly. Perhaps the illusion was breaking. Others revealed flickers of brightness in patterns too rhythmic for random physics. The data pulsed like a heartbeat, and for a moment even the most skeptical minds wondered if something living in any sense of the word had just passed us by. In late-night conferences across time zones, astronomers debated until exhaustion blurred logic and imagination. Was this breakup or birth, catastrophe or design? If 3i Atlas simply fractured, its pieces would soon drift apart and fade, destined to melt into a non-identity. But if it had released them deliberately or not, it had multiplied, and that meant intention written in orbit. Loeb summarized the dilemma in one sentence that would later be quoted in countless articles. When a comet breaks, it becomes debris. When a machine divides, it becomes strategy. Still, he urged caution. Science must not confuse beauty with proof. Patterns can deceive. The cosmos is famous for its artistry. He reminded everyone of Comet Shoemaker Levy 9, whose chain of fragments once circled Jupiter in perfect procession, a natural symmetry that had looked impossibly artificial until gravity explained it. But even he admitted quietly that this felt different. The universe had given humanity a control experiment, and now after perihelion the results were pouring in. The before had shown one object, the after now showed 4. Every data point a question mark. At a small observatory in the Canary Islands, a group of volunteers stayed awake past dawn, capturing one more sequence before daylight erased the stars. When the last image appeared, a graduate student stared at it for a long time. The main body had dimmed almost to invisibility, but the 3 fragments shone faintly in formation, evenly spaced like lanterns moving away across a dark sea. No one spoke. In the stillness, the young astronomer whispered, "If it's just physics, then physics has learned how to make poetry." And across the world, Loeb, looking at the same data hours later, nodded without realizing why. Because whether 3i Atlas had broken or given birth, the feeling it left behind was the same that we had just witnessed the universe doing something deliberate. The watchers on Earth. While 3i Atlas slipped beyond the reach of the eye, Earth watched harder than ever before. Not through a single telescope, but through thousands of them, professional, academic, civilian, and even orbital. For the first time in history, humanity had assembled a distributed nervous system capable of noticing the faintest flicker in its sky. At the center of this network stood the Galileo Project, the initiative Avi Loeb founded at Harvard, with an almost audacious premise to bring the search for technological artifacts, whether alien probes or advanced drones, out of speculation and into rigorous observation. To many, it sounded like the scientific equivalent of searching for ghosts with better cameras. But Loeb's approach was different, no belief, only data. At several secret but modestly funded sites, The Galileo project's all-sky observatories hum quietly, scanning with high-resolution optical, infrared, and radio sensors. Each installation looks like a small observatory dome beside a forest of antennas, less cathedral, more laboratory. Their telescopes capture terabytes of continuous footage, automatically analysed by machine learning algorithms that separate known aircraft and satellites from true anomalies. The system works like a cosmic immune response, recognizing what belongs and flagging what doesn't. Commercial airliners, meteor trails, Starlink satellites, these are filtered in milliseconds. But an unidentified object with unusual acceleration geometry or light curve triggers a deeper analysis, trajectory fitting, spectral classification, cross-correlation with radar and magnetometer data. As 3i Atlas began its passage behind the Sun, the Galileo project tuned its instruments to listen for echoes. If any of those hypothetical dandelion seeds drifted toward Earth's atmosphere or even toward lunar orbit, these sensors might be the first to notice. Loeb himself described the system with characteristic calm. If the universe sends visitors, we should at least be home to answer the door. The observatories were not alone. In this era of citizen science, vigilance has become communal. Thousands of amateur astronomers around the world link their backyard telescopes into online networks like Sky-Hub's Zooniverse and the Global Meteor Project. Their laptops hum through the night, sharing raw footage in real time with professional observatories. When a bright flare or a transient object appears, the data cascade across continents in seconds. A fragment passing over Arizona can be confirmed by enthusiasts in Spain before the hour is out. For the watchers, 3i Atlas is a shared obsession. Forums buzz with screenshots, stacked images, and tentative orbital calculations. Software once designed for exoplanet hunting is repurposed for comet tracking. In small apartments and mountain huts, people who will never meet nonetheless look at the same pixel of sky, united by wonder. Orbiting high above satellites join the vigil. The European Space Agency's Gaia mission, built to chart 1 billion stars, can detect slight movements of transient objects. NEO-WISE and TESS scan for infrared signatures, thermal glows that might reveal engines vents or simple outgassing. Even commercial weather satellites are retasked temporarily, their AI systems trained to recognize patterns invisible to human sight, synchronized flickers, spectral anomalies, geometric motion. This web of instruments turns Earth into what Loeb calls a planetary retina. For most of human history, we looked at the sky with naked eyes and imagination. Now sensors orbit in rings, feeding algorithms that never sleep. What we once called watching has become computing awe. The project's engineers talk about pattern entropy, a term borrowed from information theory. In a truly random sky, data scatter evenly. But if an unseen hand arranges movement, whether technological or natural, entropy dips, order appears. The Galileo arrays look for that dip, scanning through clouds of data for even the faintest glimmer of intention. To the people who built them, the goal isn't to find aliens, it's to calibrate humility. We don't assume every strange thing is technology, Loeb tells a journalist. We assume the universe is still stranger than we can measure. As the first post-perihelion data roll in this network becomes humanity's collective heartbeat. The sun has blinded our direct sight, but these machines spread from the poles to geostationary orbit continue to feel the tremors in light. In small labs, volunteers analyze their own results. A teacher in Poland, a retired engineer in California, a teenager in Mumbai. The language barrier dissolves. The sky belongs to everyone. They share frame timestamps, compare pixel drifts, argue over whether a faint point that flickered above the Andes was a fragment or a satellite flare. To watch together is itself a kind of discovery. The scale of our vigilance mirrors the scale of our curiosity, planetary, patient, and personal. Loeb often muses that perhaps this is the real lesson of 3 Atlas, not the question of alien technology or cosmic coincidence, but the reminder that the act of looking has become our species' collective ritual. We no longer gather around firelight to tell stories of stars. We gather around data streams, around shared spreadsheets, glowing in the dark, each cell a candle of its own. And somewhere at the edge of that vigilance, photons reflected off the visitor continue to fall on our detectors, tiny emissaries of the unknown, carrying not messages but evidence that we were paying attention. In that sense, Earth has never been so awake. 1 million eyes, human and mechanical, turned upward in unison, watchers waiting to learn whether what they see is the echo of a breakup or the first sign of something being born. The anomaly. Window. By the second week of November, the first unfiltered data from the post-perihelion sky began to flow like curves, radar echoes, infrared readings, all stitched together by thousands of observers in what Loeb called the anomaly window. It was the most delicate phase of the entire vigil, the moment when evidence and imagination blend like sunrise and shadow, and the world must decide what it has truly seen. Within days, reports started to multiply. A faint point of light detected near the Taurus constellation moving too slowly for an asteroid yet too quickly for space debris. A transient infrared flash over the Indian Ocean, recorded by a geostationary weather satellite and gone within seconds. A radar anomaly in Chile dismissed by technicians as a calibration error, but strangely timed with the reappearance of Three-Eye Atlas in the same sector of the sky. None of these alone meant anything. Together they formed a pattern that looked, depending on who you asked, like noise or like a whisper. The Galileo project computers flagged dozens of such events in the first 72 hours. The system categorized them 82% easily: explainable satellites, atmospheric glints, digital interference, 14% unresolved but low significance. The remaining 4% tiny tantalizing outliers earned the label possible correlation. That phrase, calm, bureaucratic, intentionally unromantic, spread like wildfire through the scientific community. Because correlation was the one word that suggested meaning without daring to promise it. For the public, however, the term carried voltage. Online forums erupted with theories: the seeds have arrived, the probes are deploying, the sky's alive. Citizen scientists shared pixelated screenshots, circles drawn in red around faint specks that could be anything or nothing at all. Some saw deliberate geometry in the alignments, others saw coincidence sharpened by longing. The professionals watching this unfold understood what was happening. Confirmation bias, that ancient companion of wonder, had entered the chat. It's the same bias that once made astronomers in the 19th century swear they saw canals on Mars and Cold War physicists mistake cosmic rays for alien signals. The same psychological reflex that turns a streak of light into a sign of destiny. Our brains are pattern-finding engines. They would rather see intention in chaos than endure ambiguity. So the Galileo analysts proceeded with caution. They knew their instruments could hallucinate too. A miscalibrated infrared sensor can invent a heat source. A timing glitch can stretch a moving object into a phantom. Even cosmic rays, those invisible bullets from the depths of space, can briefly trick a CCD camera into seeing ghosts. To protect against such illusions, every anomaly must be corroborated: different instruments, different wavelengths, different teams. 1 sighting is rumour, 2 are coincidence, 3 confirmed by independent sensors become data. But what happens when confirmation itself becomes contaminated by hope? That was the quiet tension haunting every control room. Astronomers are trained skeptics, but they are also human beings staring at a mystery that flirts with history. Each new alert on the screen stirs a pulse of adrenaline. What if this is the one? And so paradoxically, the more careful the analysis becomes, the more it begins to resemble faith. In one Galileo site outside Boston, a technician printed a radar frame that showed a faint linear cluster of 5 returns barely above noise threshold. He pinned it to the wall beside a photograph of the night sky and wrote beneath it in pencil, "Or it's just static." The humility was deliberate. Elsewhere, AI-assisted networks combed through terabytes of visual data, their algorithms designed to suppress human bias. But the irony was that they carried their own. Machine learning is trained on patterns of what we already believe exists. By definition, it struggles to recognize the unprecedented. And so the anomaly window became a kind of psychological experiment, not only about Three-Eye Atlas, but about ourselves, how we interpret wonder when it walks the tightrope between known and unknown. Media headlines swung between restraint and hysteria. Some proclaimed, "Possible new objects detected following interstellar visitor." Others countered, "Astronomers caution, no evidence of artificiality." Between those poles lay the territory where science actually lives: uncertainty, patience, repetition. Loeb's statement to the press was characteristically calm. "We are receiving more reports than usual. Most will be explained. A few may not. That's how discovery works. It begins in noise." He refused to call them objects, preferring the neutral term events. Events can vanish as easily as they appear. Still, he privately admitted that one reading intrigued him. A small object, magnitude 23, reflecting sunlight in a peculiar rhythm, 4 pulses, then silence, then 4 again. the spacing matched by coincidence or not. The earlier pattern, observed in Through-Eye Atlas's fragmentation, could be rotation, he told a colleague, could be a reflection artifact. Then after a pause, could be neither. The colleague smiled wearily. It could also be a piece of foil from a satellite. Loeb nodded, or a seed looking for soil. That phrase, half metaphor, half hypothesis, summed up the entire mood of the anomaly window. Every new blip in the data was both trivial and transcendent, a flicker that might collapse into meaning or dissolve into noise. To those who remembered history, it felt familiar. When the wow signal was detected in 1977, a single burst of radio energy astonished astronomers, only to vanish forever. When Umama flew by in 2017, its trajectory ignited debates that still haven't settled. The pattern was always the same. The universe whispers once, then goes silent, leaving us with interpretation instead of certainty. That is what the anomaly window became, a mirror more than a telescope. In living rooms and labs, people stared at the same faint specks of light and realized they were watching their own capacity for belief. Because every discovery begins as a mistake someone refused to dismiss, and every myth begins as a truth we failed to prove. The difference between them is evidence, and evidence takes time. For now, the data streams continue, the Earth still listens. And somewhere in those rivers of numbers between glitches, dust and desire might hide the first sign that the cosmos just winked back. The data blackout. The first whispers of silence began not in space, but in inboxes. At NASA's Jet Propulsion Laboratory, researchers accustomed to daily streams of telemetry from Mars Reconnaissance Orbiter suddenly found the channels empty. No images, no press briefings, no internal memos, just a short automatic notice. Due to current government funding constraints, updates are temporarily suspended. It was October 3rd, 2 days after 3 Atlas had glided past Mars, the very day its gravity or lack of it should have been measurable with surgical precision. At first, no one thought much of it. Washington was in the midst of a partial government shutdown, an all too familiar standoff where political budgets clash and civil servants wait. But to astronomers following the interstellar visitor, the timing was surreal. Within hours, the blackout spread. The European Space Agency's Mars Express team, usually prompt in releasing preliminary data, cited data pipeline delays. China's CNSA, whose Tianwen-1 orbiter had the clearest vantage point of all, issued no statement at all. Its normally active Weibo accounts fell silent. 3 spacefaring powers, each operating independently, each in possession of instruments capable of observing 3-Eye Atlas, had by coincidence or coordination gone quiet. To the public, it sounded like conspiracy. To those inside the agencies, it felt like bureaucracy at its most maddening. Here's how it actually works. Every observation from a deep space probe travels a complex route. First, the data are transmitted from spacecraft to a deep space network, massive radio antennas scattered around the globe. From there, the signals travel to mission control centers where they're decoded, calibrated, checked for errors, and then archived into internal servers. Only after multiple layers of verification and internal review are they released to the public. That process takes time, days, sometimes weeks. And when a political shutdown freezes communication budgets, even the automated systems can't publish. The antennas still listen, but the data pile up behind locked doors. Still, the optics were terrible. In the online forums and midnight podcasts, the narrative practically wrote itself. 3 nations. 1 celestial event. 0 transparency. Speculation spiraled. Some said the agencies had found evidence too extraordinary or too threatening to release. Others accused them of quietly coordinating a global embargo. The truth, as usual, was quieter and stranger. Inside ESA's mission control in Darmstadt, engineers were indeed processing imagery from Mars Express and Trace Gas Orbiter. They had beautiful crystal-clear frames of the planet's limb sunlight glinting across its thin atmosphere, and faintly a smudge that might have been the passing interstellar object. But with the world watching, even a pixel's error could ignite panic. ESA's policy forbids public release of unverified data when global interest is high. Images undergo multiple levels of peer cross-checking before publication. In other words, silence, not secrecy. At NASA, the timing was bureaucratically disastrous. The shutdown had furloughed non-essential staff, including those responsible for the high-rise imaging pipeline. Even if scientists wanted to leak the data, they couldn't. Their accounts were suspended, their systems offline. Within the agency, it was a logistical blindfold. China's situation was different. The Tianwen-1 orbiter had indeed observed the flyby region, but the CNSA has long treated such data as state property released selectively for national publications. To foreign observers, that looks like intentional concealment. To Chinese officials, it's simply standard protocol, yet coincidences have a cruel sense of timing. The shutdown, the delays, the silence, all arriving just as an interstellar object brushed the Martian orbit, a celestial event that might happen once in a millennium. Even seasoned scientists felt a twinge of suspicion. If I were writing a thriller, one researcher joked on Twitter, this is exactly when I'd cut the live feed. Avi Loeb, ever cautious, addressed the blackout during an interview. It's almost certainly mundane. Bureaucracy, not conspiracy, but science depends on transparency. When silence coincides with significance, it breeds mythology. He was right. Human beings abhor informational vacuums. We fill them with narrative. The political backdrop didn't help. Tensions between the US and China were high trade disputes. Cybersecurity concerns the quiet race for lunar resources. Each side guarded its space data like classified intelligence. ESA, caught in the middle, leaned toward discretion to avoid fueling either camp's propaganda. Thus, the world's three major planetary observers entered what analysts later called the coordinated quiet. To conspiracy theorists, it was deliberate containment. To insiders, it was an accidental symphony of red tape. Still, the symbolism was undeniable. Humanity's most powerful eyes had blinked just as the universe might have winked back. Days later, when NASA's internal channels finally resumed, the first public statement was bland to the point of absurdity. No anomalous gravitational interactions detected during the Mars conjunction event. Data processing ongoing. It said nothing, but the timing said everything. By then, the narrative had already escaped containment. Videos circulated claiming leaked footage of a stationary shadow near Mars. Talk shows invited experts to argue about hidden missions. Every gap in communication became an echo chamber for speculation. For Loeb and his colleagues, it was a grim lesson in modern science. The universe no longer reveals itself in isolation. Every discovery now passes through politics, bandwidth, and trust. The data blackout may have lasted only days, but its psychological aftershock endured. It transformed 3i Atlas from a celestial curiosity into something felt, something cultural, a mirror for humanity's deepest insecurities about truth, power, and visibility. In the end, the real mystery wasn't whether NASA, ESA, or China had hidden the data. It was why, in an age of near-infinite communication, silence still feels like conspiracy. And so, as the networks rebooted and the first official images trickled in, the question that lingered wasn't just, what is 3i Atlas? It was, who decides what we're allowed to see? The politics of silence. Silence in science is never neutral. It can be caution. It can be fear. It can even be compassion for a public not yet ready to absorb uncertainty. But silence has a politics of its own, a language that says as much by what it withholds as by what it reveals. When the data blackout surrounding 3i Atlas stretched from hours into days, the public's imagination filled the void faster than any press release could. It always does. In an era of instant information, absence itself becomes evidence. Governments know this. Space agencies too. They operate at the intersection of knowledge and narrative, where every observation has both scientific and social consequence. A pixel misread, a phrase misquoted, can spiral into a movement. So when something extraordinary looms, a signal, a comet, an unidentified object, the first instinct of institutions is often not deception, but containment. It's a reflex older than the internet. During the Cold War, astronomical discoveries were often classified not because they were alien, but because they were strategic. In 1967, when British radio astronomers first detected the precise pulses of what we now call a pulsar, they briefly considered that it might be artificial. The team labelled the signal LGM-1 Little Green Men. Before they could publish, government liaisons quietly reviewed the data, fearing that admitting even the possibility of intelligence could have geopolitical consequences. Only after verifying its natural origin did the information reach the public. Around the same time, early US satellite-borne telescopes discovered mysterious flashes over the Pacific. For months, the phenomena were top secret, not because they were extraterrestrial, but because they were actually Soviet nuclear tests. Classified research had outpaced the public's right to know. Even astronomy itself became a frontier of espionage. The Cobra Dane radar in Alaska and the Duga array in Ukraine, both built for missile detection, routinely captured celestial data that never saw daylight. Entire catalogues of orbital information sat behind security clearances, a quiet, parallel universe of classified science. By the late 20th century, that instinct to observe but not explain had woven itself into the bureaucracy of discovery. Transparency became conditional. Truth was not denied, merely delayed. The pattern survives today in subtler forms. Every modern debate about UFOs, or the sanitized term UAP's unidentified aerial phenomena, revolves around the same tension: national security versus public curiosity. The Pentagon's new All-Domain Anomaly Resolution Office, AAERO, is a descendant of this lineage, founded to study sightings, but bound by secrecy to avoid inflaming the imagination it was meant to calm. The same paradox unfolds in AI research. Corporations guard their large language models with the same opacity once reserved for nuclear codes. They justify it as safety, yet it breeds mistrust. In both cases, AI and astrophysics, the theme repeats: control the narrative, or lose control of the response. When Loeb commented on the blackout around 3I Atlas, he phrased it gently: information behaves like light. The harder you try to contain it, the more it diffracts around the edges. He understood that the real danger wasn't in what agencies knew, but in how their silence trained the public to distrust them. Science demands skepticism. Conspiracy thrives on secrecy. Between those poles, communication becomes a moral act. In the aftermath, sociologists began studying how the blackout shifted global discourse. Twitter, or what remained of it, saw spikes in searches for hidden comet, NASA cover-up, and alien probe evidence. But just as striking was the rise in searches for how space agencies release data. Curiosity had matured into meta-curiosity, not what happened, but who decides what we're told. That Loeb argued might be the deeper legacy of 3I Atlas. It exposed how science itself now lives under constant surveillance by belief. He compared it to an eclipse, not of the sun, but of trust. During an eclipse, the world grows dark, not because the sun has vanished, but because something opaque passes between it and our eyes. Institutions can become that opacity, and when they do, even ordinary data begins to glow with mythic significance. The lesson is neither cynical nor conspiratorial, it's human. Transparency is not merely a virtue, it's a stabilizer for meaning. When truth is rationed, speculation becomes currency. When experts retreat into jargon, storytellers step in with certainty. Loeb often says that the purpose of science communication isn't to eliminate mystery, it's to teach the difference between mystery and manipulation. The public can handle wonder. What it cannot handle is silence pretending to be wisdom. The blackout, brief though it was, became a case study in that delicate balance. It reminded scientists that data lives within democracy, that even cosmic discoveries light years beyond politics cast political shadows here on Earth. For the watchers, it also offered a sobering symmetry. We gaze into the universe searching for signs of intelligence, while the universe reflected through our behavior might be studying the same thing in us. In the end, the politics of silence is not just about agencies and data. It's about how a civilization manages uncertainty, whether it meets the unknown with dialogue or with doors closed. And perhaps that is the quiet moral 3I Atlas leaves behind, that the next time the cosmos sends something unexplainable, our greatest experiment won't be telescopic but cultural, a test of whether humanity has learned to see, to speak, and to listen in the same breath. The interregnum of waiting, time itself, seemed to hesitate as October 29th approached the day. 3I Atlas would vanish behind the sun the instant when humanity's instruments would be forced to close their eyes. It was called the interregnum of waiting, a strange liminal season where science, faith, and imagination all held their breath together. In observatories and living rooms alike, people counted days as though waiting for an eclipse that might never end. Astronomers, sleep-deprived and quietly superstitious, refreshed orbital charts that hadn't changed in hours. Engineers polished sensor lenses already spotless. Across continents, screens glowed in dark rooms, streams of digits scrolling endlessly across black backgrounds, numbers that measured everything except certainty. It was the calmest global anxiety in memory. On YouTube and Twitch, live streams multiplied by the hundreds. Some showed real-time solar imagery from the SOHO and stereo satellites, their feeds flickering with static bursts of coronal light. Others, more speculative, overlaid digital models of the object's trajectory, updating minute by minute with dramatic orchestral soundtracks. In chat windows, tens of thousands of viewers typed breathless messages. "We're blind now, this is it. Imagine if it slows down." Anyone else feeling weirdly emotional about a rock science had become a global vigil. Even professional institutions joined the chorus of waiting. The Minor Planet Center pinned a simple message on its website, "Observation pause until post-perihelion reacquisition." It read like an obituary. Meanwhile, in universities, students gathered for impromptu data parties, projecting sky maps on walls, passing around coffee like communion wine. In one lecture hall at MIT, an astrophysics professor dimmed the lights and played the sound of solar wind recorded by the Parker probe. "This," he said softly, "is what 3i Atlas is hearing right now." It wasn't only scientists who felt the pull. Spiritual communities ranging from meditation circles to New Age live streams spoke of alignment, energy, destiny. The object became a mirror for every human narrative, a sign, a warning, a symbol of rebirth. One Buddhist monk in Kyoto called it a teacher of impermanence, moving so fast that even the sun cannot hold it. A pastor in Texas compared it to the Star of Bethlehem, a visitor whose purpose is not to stay, but to remind us to look up. The collective psychology of the moment fascinated sociologists. They saw in it a modern ritual, a fusion of ancient skywatching and digital communion. For the first time, billions of humans share the same invisible countdown, aware of their blindness and united by it. The emotion wasn't fear exactly, it was something subtler, a mixture of awe and vulnerability. In London, a journalist wrote, "It feels like waiting for a test result from the universe." The world's mood oscillated between hysteria and serenity. On social media, hashtags like Kung Atlas Eclipse, Interstellar Visitor, and Behind the Sun trended for days. Artists posted digital paintings of a glowing ship cresting the solar horizon. Conspiracy theorists uploaded charts linking the object's orbit to prophecies, numerology, and even cryptocurrency cycles. Yet amid the noise, there was an undertone of something gentler, a quiet gratitude that in an age of division, something had managed to make the planet look in the same direction again. At the Atacama Desert Observatory, where the air is so dry that stars seem closer than thought, an astrophotographer named Inez captured her last image before sunrise. It showed the faint tail of 3i Atlas dissolving into gold, a streak of motion suspended above a line of waiting domes. She didn't upload it immediately. She simply sat outside her tent and whispered, "Good luck, traveller." In Cambridge, Loeb stayed mostly offline. He wrote in his notebook rather than on his blog, a rare gesture of privacy. His notes read more like a meditation than a paper draft. Waiting is the most human experiment. We stare into light too bright to see, hoping the darkness beyond it will be kind. Meanwhile, on the far side of the world, the Galileo project's automated systems continued scanning their instruments, unaffected by human impatience. They logged sensor readings with cold precision, yet even the scientists monitoring them confessed to feeling something akin to suspense, an emotional state no algorithm could quantify. As the final hours approached, television anchors adopted a tone somewhere between documentary and prayer. "The object is now entering the solar corona," one announced, her voice steady but her eyes glimmering. The broadcast cut to a live composite from NASA's Solar Dynamics Observatory, a torrent of plasma arcing outward, brilliant and indifferent. Somewhere in there, she whispered, is our visitor, and then nothing. Just solar wind static and the long exhale of collective silence. Around the world, people stayed up late watching streams that showed nothing at all, just the sun burning against blackness while chat messages slowed one by one into stillness. It was a strange peace that shared ignorance, a kind of global meditation on the limits of knowing. In the last minutes before dawn in North America, Loeb posted a single sentence on his public feed. For the next few weeks, the universe speaks without witnesses. It was retweeted millions of times. For the first time in living memory, humanity wasn't watching an event, it was waiting for its absence to end. And in that waiting, something rare happened. The world felt small again together under one invisible sky, hoping that when the light returned, it would still mean wonder, not warning. The reemergence. For weeks, there had been only the sun, its furious brilliance, its veil of plasma, its indifference. And then, just before dawn, on November 17th, the first shadow returned to the map of light. At the European Southern Observatory in Chile, a telescope operator named Elise stood in the pre-dawn chill eyes fixed on a monitor as algorithms combed the new frames. The desert air was utterly still, a silence so vast it felt sentient. Somewhere beyond that horizon, in the glare where human sight fails, 3R Atlas was about to re-emerge. Across the world, observatories stirred like sleepers sensing morning. In Haleakala, Hawaii, the Atlas survey dome opened with a mechanical sigh. In puny Canary Islands, an Arizona telescope slewed toward the coordinates calculated weeks earlier. Their cameras were already running, capturing the first photons to escape the sun's blinding embrace. The data trickled in slowly, lines of numbers, not beauty yet. But inside those lines, the watchers searched for resurrection, one point of light, where there had once been one, or perhaps four. Would the object reappear whole, or fractured, or transformed? Would it shine as before, or pulse with some new inexplicable rhythm? Would it still be there at all? Astronomy rarely feels cinematic, but this morning did. Each observatory sat in its own dawn, Chile bathed in apricot light, India touched by the pale blue of monsoon haze, Arizona glowing pink against sandstone, and yet all were joined by the same trembling expectancy. A planet turning its telescopic face toward the sun, not in worship, but in curiosity. On the screens, faint glimmers began to rise from the noise floor. First a false alarm, a satellite flare, then a meteor trail, then something steady. The operator called out softly, "Target reacquired." The words rippled across radio channels, message boards, and data feeds. Somewhere Loeb's phone vibrated. He didn't check it immediately. He was outside under a cold New England sky watching the dawn without instruments. What the telescopes saw in those first images would take hours to confirm, days to interpret. The light was faint, about 2 magnitudes dimmer than before. The object or its remains appeared elongated, a streak, not a dot. But within that streak were 3 bright nodes spaced evenly, almost symmetrically. It could have been an illusion. It could have been truth. Analysts worked in reverent quiet. They cross-referenced exposure times, checked for cosmic rays, reran calibrations. The usual discipline of skepticism. But even as they did, an undercurrent of awe crept in. In the break rooms of observatories, scientists watched dawn climb their windows and felt something. They could not quantify a pulse that matched the cadence of the images. Because whether it was one object or 4 debris or design, it had come back. It had survived the fire. The world awoke to headlines half factual, half poetic. Interstellar, visitor returns to view. After the sun, what the skies reveal. Live streams reignited. Chat windows filled again. People everywhere leaned closer to their screens as though proximity could increase certainty. In Chile, Elise whispered, "Welcome back," before sending her data upstream. No scientist would call it a miracle. But in a quiet sense, it was because the moment confirmed that Curiosity too had survived the inferno. Later that night, Loeb would describe it in a brief post that went viral. Every dawn is a controlled experiment. You go to sleep not knowing if the light will return, and every morning it does. Today, we looked at the sun and found our question still waiting for us. The re-emergence of 3I Atlas did not bring clarity, not yet. Its trajectory would need days of triangulation, its structure weeks of analysis. But it brought something rarer than answers continuity. As the first daylight touched the domes in Hawaii and the Andes, technicians powered down their instruments. The sky above them glowed with the thin gold of morning, the same hue that had hidden their quarry for so long. The hum of the computers softened. The waiting for now was over. In every direction the sun rose, and in its wake, somewhere between the orbits of Mercury and Earth, a faint glint kept moving, still nameless, still indifferent, still ours to wonder about. The outcome and the lesson. In the weeks that followed, 3I Atlas's return to visibility, the world learned something strange. Data can illuminate everything except certainty. The object had survived. That much was clear. But what it had survived as comet relic or something in between remained open to interpretation. The telescopes agreed on a few facts. Its brightness had diminished by nearly 60% since pre-perihelion. Its trajectory, though slightly altered, stayed gravitationally consistent with known physics. Fragments persisted, 3, perhaps 4, holding their spacing as they drifted outward from the sun. The symmetry was either coincidence elevated by hope or intention disguised as chance. The evidence, like all great evidence, pointed in 2 directions at once. The natural interpretation. If 3I Atlas was a natural comet, then nature itself had outdone imagination. Its hollow interior, slow spin, and improbable survival would force a rewriting of models for interstellar material. Scientists would call it a Type IIs, interstellar aggregate, a frozen foam of ices and dust so porous it behaves more like smoke than stone. It would show that the universe is far more inventive than we allow, that between stars, fragile objects can travel for millennia, without disintegrating, carrying chemistry from one sun to the next like spores in the cosmic wind. Such a finding would not disappoint. It would echo the joy of discovery that followed the first exoplanet in 1995, when what had been unthinkable for centuries became ordinary within years. It would remind us that alien doesn't have to mean artificial. Sometimes strangeness is simply the texture of reality we hadn't yet resolved, and it would humble our longing for drama, proving once again that nature without intention creates patterns so exquisite they trick us into seeing purpose, the engineered interpretation. But if the symmetry held, if micro-accelerations and stable trajectories confirmed deliberate motion, then the universe would no longer be theoretical. It would be populated. Not in the cinematic sense of invasion or contact, but in the quieter, more unsettling sense that intelligence has already passed through perhaps eons ago. Humanity would face its second Copernican moment. The first dethroned us from the center of the cosmos. This one would dethrone us from uniqueness. Just as Galileo's telescope turned gods into moons and Kepler's ellipses replaced perfect circles, the recognition of an engineered interstellar artifact would end the illusion that thought belongs only to Earth. The implications would be profound yet strangely practical. We would not hear voices or receive messages. We would inherit proof without context, a silent technology adrift in time. It would force philosophy, religion, and science to share a table again, to speak not of conquest but of continuity, that mind itself may be as natural to the universe as gravity. And yet even this revelation would contain humility, because the artifact, if artifact it were, is ancient. It would mean that intelligence once existed, built scent, and was forgotten, its emissary now mistaken for ice and dust. We would be the latecomers reading the graffiti of civilizations gone quiet. The lesson, in either case. In truth, both outcomes lead to the same horizon. Whether 3 Atlas is a comet sculpted by physics or a construct sculpted by thought, it teaches the same lesson that wonder is renewable. Our instruments may change, but our reaction to the unknown does not. When Copernicus first wrote De Revolutionibus Orbium Coelestium, he hesitated to publish, fearing ridicule. The church, the scholars, even fellow astronomers resisted, yet his humility before the data, his willingness to move Earth itself, changed history. When astronomers discovered the first exoplanet orbiting 51 Pegulae, many dismissed it as noise. The data were too clean, the signal too precise. Only later did we realize that planets were not rare at all. We simply hadn't learned to see them. So too with 3I Atlas. Perhaps in 50 years we'll look back and smile at our caution, our endless debates, our obsession with possibility. We may catalogue 100 similar visitors by then, some natural, some perhaps not. And this first interstellar enigma will seem like the opening sentence of a much longer conversation. Loeb often summarized it best. Whether we found a comet or a craft, the real discovery is the same, that our curiosity still outpaces our fear. That sentiment spread quietly through observatories, classrooms, and online forums. The object's physical nature mattered less than the psychological milestone it marked. For a brief moment, humanity remembered how to wonder collectively. No war, no ideology, no border could monopolize the question. What if? When the final reports were published months later, their tone was cautious, almost tender. The conclusion read, "The data remain consistent with both a low-density interstellar body and an engineered shell. Further observation required. No resolution, no final act. Only the admission that the cosmos had given us a question, not an answer." And maybe that was the real outcome, the rediscovery that science itself is a story told in installments, each revelation a comma rather than a period. As the last lines of the report circulated, dawn broke over the Chilean desert once again. Telescopes turned westward, their mirrors still warm from the night's vigil. The sky was empty now, save for sunlight. Yet in that emptiness lingered the shape of something once seen, once questioned, never forgotten, a small light that had travelled unimaginable distances, only to remind its observers that ignorance when faced honestly is the beginning of wisdom. The ethics of naming the unknown names are the first fences we build around mystery. Before we understand a thing, we name it so we can point discuss, and pretend the act of description equals possession. But every label, however useful, also limits what we allow a phenomenon to be. From the moment 3i Atlas entered the public vocabulary, the struggle over naming began. Was it a comet, a probe, an object, or a visitor? Each word carried its own gravitational field of meaning, tugging the mind toward a different universe of implication. Comet is safe, familiar, domesticated by centuries of observation. It conjures icy nostalgia, not danger. Artifact, by contrast, awakens a primitive pulse in the brain, the same one that flared when humanity first imagined gods descending in fire. Visitor sits between them, balanced and ambiguous, a word that humanizes without proving humanity. Avi Loeb preferred object, neutral, clinical, unpoetic. We should describe what we know, he said, not what we wish. Yet even he admitted that language shapes expectation. Once an object becomes a visitor, it inherits intention. The imagination, uninvited, takes its seat at the table of evidence. This tension between awe and alarm is not new, it's the rhythm of science communication itself. When Halley's Comet returned in 1910, newspapers printed lurid headlines about cyanide in its tail, selling gas masks to terrified citizens. When the first UFO reports surfaced after World War II, the US Air Force labeled them flying saucers, not because they resembled saucers, but because a single witness compared their motion to one and language fossilized perception. And in 2017, when Oumuamua appeared, the word cigar-shaped spread faster than the data that disproved it. Media doesn't just report discovery, it manufactures metaphor. Scientific literacy is the immune system of wonder. It lets awe survive without infection by fear. But in an attention economy, ambiguity sells. A comet that behaves oddly is a footnote. An interstellar probe is a headline. The difference is not evidence, it's marketing. Loeb knew this, and his relationship with the press reflected the paradox. His insistence on open speculation made him both admired and attacked. To some, he was a pioneer of intellectual courage. To others, a scientist flirting with myth. Yet what he demanded above all was permission to ask improbable questions without being dismissed as unscientific. He reminded journalists that uncertainty is not ignorance, it's honesty. When you don't know what something is, he said you should name the mystery, not the monster. The ethics of naming then lies in restraint. To call 3i Atlas an artifact without proof is to invite hysteria. To call it merely a comet when evidence strains against that simplicity is to commit erasure. The middle way, acknowledging possibility without collapsing it into story, is harder but truer. This challenge extends beyond astronomy. The same dilemmas play out in AI research. Climate science and medical crises language determines how the public feels before facts can educate them. Machine learning sounds benign. Artificial intelligence sounds prophetic. Global warming ignites panic. Climate shift sounds like weather. Words decide whether society reacts with curiosity or paralysis. When science meets mystery, humility must become editorial policy. That is why some researchers began calling 3i Atlas not a comet, not a probe, but simply the interstellar object. The phrase may sound sterile, but its emptiness is ethical. It preserves space for discovery to breathe. During a symposium months later, Loeb offered a reflection that bridged linguistics and morality. To name too soon is to colonize. We must let the unknown name itself through evidence. The audience was quiet for a long time after he spoke. Perhaps they felt the truth of it not just as scientists, but as humans who name, categorize, and control by instinct. Because naming is power, and power over the unknown carries responsibility. What would it mean if one day we confirmed 3i Atlas as artificial? Would we still call it a visitor if no one answered its knock? Would we still call it alien if its makers were extinct? Or would we simply call it ours because discovery itself makes everything human again? Language cannot be neutral, but it can be careful. To speak of the unknown with precision and compassion is the closest science comes to prayer. When the final joint report on 3 Atlas was released, its closing sentence felt less like data and more like benediction. The object remains unclassified. Its story continues, no triumph, no panic, just humility, our oldest and most reliable instrument, and perhaps that is the ethical horizon toward which all science should aim to speak with awe but not alarm, to name without claiming, to describe without deciding, to let the universe remain for a little longer what it has always been, larger than our words. The threshold of mystery. There comes a point in every investigation when numbers give way to silence, when even the most precise instruments begin to resemble prayer. 3i Atlas has passed that point. It now drifts beyond the orbit of Earth, farther each day, a dim ember against the sun it once dared to approach. Its light fades, but the question it carried does not. In the end, perhaps the object's greatest revelation was not about itself, but about us, how easily we awaken when mystery calls our name. For months, humanity turned its collective gaze to one speck of sky. Scientists watched children, imagined skeptics, calculated dreamers waited. And in that brief alignment of curiosity, the world became whole again, not because we understood, but because we agreed to wonder. That is the quiet miracle of science. It binds us not through certainty, but through shared uncertainty. A comet, or a craft natural, or made those distinctions dissolve against the immensity of the question itself. The cosmos didn't need to answer. The act of asking was enough to make us infinite for a moment. In Cambridge, Loeb would later write that 3i Atlas reminded him of how discovery really feels not the trumpet blast of revelation, but the soft intake of breath before comprehension. Knowledge, he said, is the shadow mystery casts when it passes near the light. The world eventually moved on. Headlines dimmed, forums quieted, live streams ended, yet somewhere data still trickles in tiny corrections to an orbit, a final glint caught in a deep space image. The story never closes, it just thins into background like starlight at dawn. And perhaps that is how all mysteries end, not with resolution, but with absorption. They become part of the rhythm of our awareness, the slow pulse that keeps us asking. Look up tonight, and the sky will seem unchanged. But between those familiar constellations drifts the memory of an object that made us feel small and awake and beautifully unfinished. We may never know if it was alive or engineered or merely improbable, but we will remember what it did to us, how it reminded a restless species that not knowing is not a failure, it is a form of participation. So let the telescopes rest. Let the data archives hum softly in the dark. Let the mind settle into gratitude for the watchers, the instruments, the long patience of inquiry. Because mystery is not the absence of knowledge, it is the presence of possibility. It is the quiet invitation to stay curious even when the sky goes blank. It is the universe whispering through objects and orbits and silence itself that the story continues beyond the frame. And as you close your eyes as the hum of machines fades into night, remember, perhaps mystery is how the universe keeps us awake to wonder. Thank you. Subscribe now and don't miss what's to come.